I welcome all of you to the sixth day of our program, 10 days FDP on optimization techniques, theory and practices in engineering in emerging applications. So today we are having two sessions. On the first session, I am going to discuss about another two optimization algorithm. One is your harmony search algorithm and the Firefly algorithm. And the second section, Dr. Paningda is going to discuss about well optimization algorithm and its application in deep learning along with some time series data. Okay, let's start. So am I audible? My PPT is visible.
Yes, madam.
So let's start this harmony search algorithm. So in this session, we are going to discuss about one nature-inspired algorithm, that is the harmony search algorithm, and another swarm-based intelligence algorithm, that is the Firefly algorithm. So we'll see how this harmony algorithm works, right? Algorithm search algorithm works, how the music phenomena is inspired or mimicked into the optimization problem. Then we'll see what are the various steps through which we can moving towards the global solution in the harmony search algorithm. Then we'll discuss some of the improved version of the harmony search algorithm, and then we'll go towards the Firefly algorithm and how the Firefly algorithm works, what are the control parameters in the Firefly algorithm, and what are the applications of this harmony search algorithm and Firefly algorithm. As I told, the harmonic search algorithm, this is mimicking the nature, right? How music, the musicians learning music, right? That phenomena is mimicked into this harmony search algorithm. So the relationship between music and mathematics that is modeled by the various phases in the harmonic search algorithm. So generally what harmony means, it refers to the sound request caused from two or more musical instruments when the musicians playing at the same time. Right? So generally the harmony, right, or the pitch of the sound, it evaluates the relationship between two or more musical instruments. So the musical, right, the music phenomena or this inspiration, this we are modeling through this optimization algorithm, and that is our harmony search algorithm. So how the musicians, right, they are improving their skills, right, to rehearsal to rehearsal they are doing. Music band improves through rehearsal to rehearsal, and the harmonic search algorithm through the one iteration to another iterations, we are going to improve the solution of a particular problem. If you compare that the relationship between what are the comparison factor between these musicians and this optimization process, right? So each musician, right, or each musician is playing one musical instrument. So the decision variables, it may represent one musician or one musical instrument. So here constraint is that one person is using one instrument only, right? So those are the decision variables for the optimization problem. So each musician plays a note, right? So a note means that is the value of the decision variable. Right? So what is our target? The musicians, they are trying to find out the best harmony altogether. That means they have to see the combination of all the musical instruments, sound produced by all the musical instruments at the same time. So here what it is our target? Our target is to find out the values of the decision variables at a time, which will provide the global optimum solution for our given problem. Okay? So there are different, right, the mapping between your music and the optimization problem is it modeled through different comparison factors. Right? If you see the target, what is the target in the harmony or the music, and what is the target in the optimization process? So in the music, right, the harmony improvisation, right, and the optimization process. So in the music, the target we are defining by a aesthetic standard. So this is the right term related to your music. And the optimization process, what is our target? Our target is the objective function. We want to either minimize the objective function or we want to maximize the objective function. So the next factor is best state. So best state means the best harmony, or that is the fantastic music we are telling, right? So that is your best state represents to music. So the fantastic harmony, and in the mathematical optimization process, best state means that is our global optimum solution. Right? So here the components, right? What are the uh, musical instruments and what are the pitches of the sounds produced by those musical instruments? Those are related to your music, and the values of the decision variables, they represent the components in the optimization process. So the decision variable, either it represents a musician or it represents a musical instrument. So our assumption, we are considering that one musician is playing one musical instrument at a time. So the process unit, if you consider this factor, so each procedure of the musician, that is a process unit, and each iteration, that is called the process unit in the optimization process. Then what they are doing, this is the music and the optimization. So the musicians, right, they are playing a note from one harmony to another harmony. So harmony means the combination of sounds produced by different musical instruments at the same time. And the optimization process means what? We have to select the new values or the variable values from the harmony memory. So from the harmony means from the previous iteration. It means in the optimization problem. Second is, right, so always the musicians, they are trying to play a note which is close to another one stored in the memory. Right? But here in the optimization process, how that is similar, it replaces the new values with other values that are close to the current values. Right? So we'll see through an example how these things we can compare, we can model in that optimization process. Right? So like we are having in the optimization process, we are having the lower bound and the upper bound of the decision variable. Every decision variable we are considering the upper bound and the lower bound. So what it represents in the music, it represents the musicians have to play a random note from the possible ranges. So for what is the range through which the musicians can play a note. Right? So here that means the new variable values are randomly selected from the possible range. So this possible, it corresponds to the the lower bound and the upper bound of each decision variable in the problem. Like that, every instrument they are having some range, right? In that range, the musician can play a note. That is the meaning here. Right? Now, this is, as I told, so this is a population-based meta-heuristic algorithm, and generally this is coming under your nature-inspired algorithm, and it is inspired from the musical process of selecting for a perfect state of harmony. Right? So, meta-heuristic and heuristic, as I have discussed, right? Meta-heuristic, that is the heuristic about the heuristic, and we are using some high-level design technique, right, to select a solution or for the heuristic. Okay, so this is proposed by Game et al. In the year 2001. Okay, so that aesthetic quality we have seen in the comparison factor, right? So the pitch of each musical instrument, it determines the aesthetic quality, right? Just as our fitness function or the objective function value in the optimization problem. So what is the use of this fitness value or the objective function in our optimization problem? That represents the quality of the decision variable. That means the solution, the quality of the solution. Okay. So in the music improvisation process, when the musicians, they are producing notes, so all the players sound pitches within the possible range, right, in order to make a good harmony. So that is the lower bound and the upper bound of the values of the decision variables. So if all pitches make a good harmony, each player stores in its memory, right? That means if it is a, right, it's a combination of, suppose this is a musical instrument MI1, MI2, MI3. So the musicians there, right? Three musicians are there. They're producing, suppose, different notes for this instrument, different notes for this instrument, different notes for three instruments. So this combination, right? If this combination is producing a good harmony or a good solution, right? That is the you have to determine in the music with respect to your aesthetic quality, and with respect to the optimization problem, we are calculating the fitness value or the objective value. Right? So this is the combination. This is all the pitches make a good harmony. Each player store in its memory because that is a best harmony. So the musicians they will try to mimic that harmony. Right? So that experience and the possibility of making a good harmony is increased next time. So if the musicians they will try to improve themselves, they have to use the existing harmony in the memory, and by the time with respect to time, right? They will able to generate a good harmony in the near future. So in optimization, how we are doing in the every population based meta heuristic algorithm, whatever we have discussed so far, right? Whatever it may be the GA, it may be the TLBO, it may be the RAO algorithm, it may be the PSO, right? It may be the D or it may be the ABC, whatever. So every algorithm we are selecting or we are generating the initial solutions randomly, right? So here also, right, but within the some range depending upon the lower bound and the upper bound, we are generating the initial solutions randomly. So here also in the music process, all the musicians they will generate the music, right, through the musical instrument randomly. That means that pitch of the pitch of the sound produced by every musical instrument will be generated within the possible range. So this range we have to define. That represents the LB and the UV value for the decision variables in the optimization process. So if the objective function value of these decision variables is good, that means how we will determine how this objective and decision how these decision variables are good. For that we have to determine its objective value, right? If this is good, that means we can consider that is a promising solution or that is a better solution than the previous solution, right? So if you do for a number of iterations here, so whatever initially you are generating the solution or whatever music you are generating initially, right, after a few number of iterations, maybe you are getting the best music or you are getting the best harmony, right? So that's thing. So every heuristic or the meta heuristic algorithm, what we are doing, we are applying some intelligent operators, right, intelligent operators for determining the heuristic, how to guess for the next solution. So what are the intelligent operators? Like we have seen in the genetic algorithm, we have applied selection, right, crossover, mutation. In the differential evaluation, we have applied mutation, recombination. ABC, we are doing the employee V phase, onlooker V phase, scout V phase, right? PSO, we are doing the position update, velocity update. So these are the intelligent operators are defined inside that meta heuristic algorithm in order to explore the source space. Similarly, in this harmony search algorithm, there are some intelligent operators we have to use to generate good solution from one iteration to another iteration. So what are the equations here? Let us see the simple SSA algorithm is very simple, right? So only one mathematical operation you have to perform and randomly you have to generate the solution, right? So we'll see how we have to solve a problem by using this harmonic search algorithm, right? So first there are certain terms here, right? One is your harmony memory, right? So we'll go one by one. Harmony memory is there, right? So the harmony memory, it contains a number of harmonic memory vectors, right? HMV or HMS vector, you can call this as, right? So like your population based, we have defined as this HSA, harmonic search algorithm, is a population based algorithm. We are doing in the GA, we are defining population size equals to 10. That means 10 chromosomes we are initializing, right? And in the PSO, suppose we are defining 10 particles are there. That means our population size equals to 10, right? So in this harmonic search algorithm, that population is called your harmony memory. So this is my harmony memory, right? So the harmony memory consists of number of harmonic memory search vectors, right? So if the HM value equals to 10, it means there are, right, the memory size is 10. So 10 HMS vectors will be there in the memory, right? So that is the right your initial population you are generating. So here you are generating the initial population, that is the harmonic memory, right? So the initial population is the harmonic memory, which contains a number of memory search vectors or the HMS vectors, right? So like every population based algorithm we are generating randomly, here also we have to generate the HM or the harmonic memory randomly. If you see in this diagram, now you see this x11, x12, x1n, right? And in the right, these are the columns, and there are how many rows are there? HMS1 number of rows are there. You see HMS1, HMS2 up to HMS1. That means number of columns are n, right? Number of columns in this matrix, or the size of the matrix is HMS size into cross n, right? So number of rows equal to HMS. So this harmonic memory size you have to define. If the harmonic memory size equals to 10, that means the population size equals to 10. So 10 harmonies we are producing. So each row it represents one harmony, or you can call this is the harmony vector, right? So how many musical instruments are there here? There are n number of musical instruments. This is the first instrument. This is the second musical instrument. This is the nth number of musical instrument, right? And what this represents, this value x11, x21 up to x HMS1. So these are the pitches of the sound produced by the first musician if the musician is playing the first musical instrument. Similarly, x1n, x2n up to x HMSn, this represents the n number of pitches of the sounds produced by the nth musician by playing the nth musical instrument. So this represents the pitch of the sound or the pitch of the music produced by the musician by playing that instrument, right? Now what this harmony represents, so this one harmony represents one row, right? That's why the HMS size, harmonic memory size equals to 10. So one row, this is called a harmony. That means the musicians, they will try to find out a music by the combination of, or if they will play all the musical instruments at the same time. So their target is to find out a good harmony in the harmony memory. So similarly, in our optimization problem, we want to find out the combination of this n number of decision variables at a time, which either minimize or maximize our objective function. So this is the first step you have to do in the harmonic search algorithm. You have to define the HMS vectors, right? That the harmony memory size. Depending upon that, those many number of harmony you have to keep in the harmony memory, and the number of musical instruments or the number of decision variables also you have to define here, right? So there are different terminology are there in the harmonic search, right? So the musicians, they have to improve the music, right, with respect to time. So that improvisation of the harmony, it takes place by using one parameter, that is your harmony memory consideration rule, that is a HMCR. So this value, right, this value always the range of this parameter, always it will, you have to take in the range 0 to 1, like a probability value, right? So what it represents, harmony memory considering rule means it will determine, right, the musicians, they have to choose, right, the pitches of the sound and a harmony from the existing harmony memory, right? So HMCR, this is the probability of choosing value from the historical value stored in the harmony memory. So generally this is 0 to 10, but if you see the research papers, generally your 0.7 to 0.95, they are getting the good results. So you have to properly tune this parameter HMCR for your problem to find out the good solution. So how to determine, once we have generated this solution, right? So in the next iteration, we have to generate a new harmony, right? So for that, what you have to do? So depending upon that HMCR, we are going to change the solution here, right? So for that, you have to generate a new random number R1. Okay, so this is a stochastic nature of the HSA. You need random number you have to generate, and always all the random numbers whatever we are generating in this meta heuristic algorithms, generally they follow the uniform distribution in the range 0 to 1, right? If this random number is less than the HMCR, that is the harmony memory consideration rule, that means for the first musical instrument, right, you have to choose the pitch of that first musical instrument from the harmony memory itself. Now, if you see, so there are n number of musical instruments are there. So, in order to improve the pitches of the sound produced by the suppose this musical instrument, right? In the next iteration for the first musical instrument, we have to generate a random number R1, right? So what is the value? So one new harmony we are going to generate. So new harmony means it consists of n number of values only. Harmony means a vector, this row. Okay. So what is the value of this first musical instrument or the first decision variable, right? So how to determine whether you can use this harmony memory or you can generate a random number. So how to decide that one? For that you have to use the HMCR value and a random number. And if the random number suppose R1 equals to 0.5 and our HMCR value suppose we have defined as 0.8. So this R1 is less than your HMCR, right? So the musicians, they will try to find out a pitch out of this pitches produced by the musical instruments for the HMS number of vectors. So here X11, X21 up to X HMS1 is there, right? So out of this HMS number of vectors, one value it will choose randomly, any value. Suppose it is taking the X21 value. Like similarly for R2, for the second decision variable or the for second musical instrument, again you have to generate random number. If it is less than HMCR, again you have to use any one of the value from the second musical instrument. So in this way, you have to generate one value for every musical instrument, right? In this memory improvisation process. So what happens if your random number, whatever you are generating, this is greater than HMCR? So that condition we will see later. Let us first see if, because they are trying to improvise the new harmony. So what will happen if the random number is less than your HMCR? So any one value stored in the HM, right? For that particular instrument or for that decision variable we are choosing. So that is the any value we are choosing here, right? This is the equation. Then what you have to do, if you are choosing the harmony memory, right? Next you have to adjust the pitch of that musical instrument. I mean the sound produced by that musical instrument. So for that, there is another parameter, that is the pitch adjusting rate. So what happens here? The often decision variable from the HMCR, whatever you are selecting from the harmony matrix or the harmony memory, this is further examined to understand whether we have to need the pitch adjustment or not. Right? So the pitch adjustment will be done by using this PAR factor. Right? So this PAR factor, this is also you have to generate or you have to initialize in the range 0 to 1. Generally, you have to keep a high value, right? So if R2, right? So how whether you have to adjust the pitch of that harmony or you have to discard, right? So how will you determine? Again, there is a random number you have to generate, and if that random number is less than your pitch adjustment rate, so you have to adjust the pitch of that musical instrument, right? So how do you have to do? So for that, this is the new value of the harmony, right? Or the musical instrument. This equals to old value. So this plus minus, this either you can use plus, you can use minus. It depends upon what is your objective function, right? If your objective function is the maximization, right? Always you try to maximize. It depends upon the objective function, right? What type of objective function you are using, right? And if you're simply, suppose our sphere function we are using, right? For the sphere function, if you want to minimize, so we have to use this minus, right? If you want to suppose maximize something, simple function is that you have to see plus, right? So depending upon the objective function, you have to decide whether you have to do the addition or you have to do the subtraction. So the new value equals to old value, right? So plus or minus you can use. Then you use a random number in the range 0 to 1 into this is the bandwidth. So the bandwidth you have to multiply with the random number. Then the total value you have to add with the old pitch to produce the new pitch. Right? So where your BW is the bandwidth factor, which is used to control the local search around the selected variable in the new vector. So this is your exploitation, right? We are trying to exploit, right? So that is the bandwidth. By using the bandwidth, we are trying to exploit our solution space. Suppose, so this we have seen, right? Next, like every optimization algorithm, after doing this one, what we have to do? So this if new value is better than the old value, so you have to accept the new value. If this is not a better solution than the old value, So you have to keep the old value in our vector, right? Same thing we have to apply here. Now let us see, this is the what with the other part, right? If initially if your random number is less than your harmonic memory consideration rule, right? We are adjusting the pitch of the sound produced by the musical instrument. So what happens if your R1 less than HMCR fails? That means if your R1 is greater than HMCR, that means the musicians will not take any pitch produced by any musical instruments from the harmonic memory. Right? So randomly they will play a note. That is the meaning. So if the condition R1 less than HMCR fails, I mean the H1 R1 is greater than the HMCR, so the decision variable value has to be generated randomly. And randomly always we know, right, how we are using depending upon the lower bound and the upper bound of the solution and a random number. We are generating a solution randomly in every optimization algorithm, right? So xi is a new will be, right? So the lower value of that decision variable, lower bound plus upper bound minus lower bound. See the multiplication, right? Multiplied by a random number you have to generate in the range 0 to 1. Right? So this is the difference. So there is no pitch adjustment factor here up to whenever you are doing the random initialization, right? Because you don't know what will be the objective function. So there is no pitch adjustment. So there are different, right, modifications in the basic harmony search algorithm where after doing, right, randomly choosing the solution also, they are doing the pitch adjustment rate. Same thing they have to do here also, pitch adjusting rate. But the basic harmonic search algorithm, if you are randomly choosing the solution, there is no pitch adjustment. Okay, so what you can use that one also, and you can verify whether you are able to generate better solution in the subsequent iteration or not. So whatever I told you, this L is the upper lower bound and U is the upper bound for the given problem. Next, what you have to update the harmony memory, because harmony memory with the size of HMS, we have generated the matrix initially. Then we have applied the improvisation of that harmony, right? By using the random number R1. If R1 is less than HMCR, we are doing the pitch adjustment, right? So for that, if R2 is less than your pitch adjustment rate, we are doing the pitch adjustment by using the bandwidth, right? If your R1 is greater than the HMCR, random solution we are generating and we are not doing the, let us assume we are not doing the pitch adjustment. And here also we are getting the solution. Either this case will occur or this case will occur. So here you are generating a new solution. So you have to update the harmony memory in every iteration, like you are updating the population in every iteration in all the whatever algorithms we have discussed so far, right? Here also you have to update the harmony. So harmony memory updating means the harmony vector, right? Whatever your new vector you are generating, right? So that vector you have to introduce into the harmony vector, harmony memory. So how you are going to introduce? So this harmony memory updating rule is different than the whatever algorithms we have discussed previously, right? So once you have generated the harmony vector, new vector, so it will replace the worst solution or the worst harmony vector in the harmony memory, right? So how will you determine which one is best? If x new is best, you have to replace the worst solution by this x new, right? If it is not best, right? So the old whatever is there in the previous, that will be retained, right? So it will replace the worst harmony vector in the harmony memory if its objective value is better than the objective function value of the worst harmony. So how to define better? Again, it depends upon whether you are doing maximization or you are doing the minimization of your objective function, right? So for the minimization, you know, if the new value is less than the x worst, so what you have to do, you are updating only one HMS vector in the HMS memory, right? That means you are selecting the worst solution in the harmonic memory and you are updating this worst solution with the new solution if that new solution is better than the worst solution, right? That means we are trying to avoid the best solution, right? In every iteration that we are moving away from the worst solution. That is your called exploitation. We are trying to do the exploitation in the harmonic memory. And how we are doing the exploration? By doing the pitch adjustment rate, we are trying to do the exploration. So in this way, you have to do the trade-off between your exploration and the exploitation, like other optimization algorithms, right? So this is the memory harmony memory update. So this is the procedure only. So this thing you have to write. Whenever you replace the worst solution with the new solution, again you will get another harmony, right? You are getting another harmony. So with this harmony, again you have to repeat the procedure till your termination criteria is satisfied. So at the end, whatever harmony you are getting, right, having HMS number of vectors, whichever is best, right, that will be your optimal solution for the given problem. Okay? So this is the basic algorithm for this HSA. So you have to initialize the parameters, harmony memory consideration rate, pitch adjustment rate, bandwidth, harmony memory size, maximum number of iteration, what is the dimension of the given problem, right? So you have to generate the initial harmony memory randomly by using the, here you can keep the lower bound and the upper bound also, okay, L and U. Then what you have to do, you have to evaluate every harmony, right, using the fitness function or the objective function. So you can find out the worst solution, right? So this best and worst, it depends upon your minimization and the maximization, right? So the inferior solution you are finding here. Next, what you are doing? So you have to iterate for a maximum number of iterations. So some procedure you have to follow. You have to improvise the harmony. You have to you have to adjust the pitch. Then you have to replace the worst harmony with the new harmony if the new harmony is better. So same thing, whatever we have discussed. If random number is less than your HMCR, you are choosing the existing harmony, right? Redundant you are choosing. Then what you are doing? If for pitch adjustment, again you are generating another random number. If that is less than PAR, pitch adjustment rate, you are adjusting the pitch randomly. We are using the bandwidth, right? Else, so this is for your improvisation of the existing harmony memory. Else, if the random number is greater than your HMCR, you are generating the random harmony, right? Then the new harmony you are comparing with the worst harmony in the harmony memory. Then what you are doing? You are replacing, right? You are replacing the worst harmony with the new harmony. So after doing the maximum number of iterations, you are returning the best harmony as the optimum solution. So this is the basic algorithm or the basic steps you have to follow, right? Whatever, right? Whatever I explained, everything is there here. And even the procedure step one is written. So parameters you have to initialize. This is the counter, right? For the maximum number of iterations. For every harmony memory, right? For every musical instrument, sorry, for every combination of, right, all the harmony size, you have to generate the initial population. Then you evaluate the fitness factor, right? Then you have to, right, you have to generate a new solution. How you have to generate a new solution? For every number of harmony, for I equals to 1 to I less than equal to HMS harmony size, right? Then for every decision variable you have to do that harmony improvisation at the pitch adjustment. So for j equals to 1 to I less than equals to 2. So this is for your population size if you compare, right? And this is for your dimension of the given problem, right? So if I R1 less than HMCR, so you are taking the new value from the harmony memory from HM, right? If you are taking from the harmony memory, then you have to do the pitch adjustment. So this is for the pitch adjustment. R2 less than PAR. So this is the plus minus, right? And this is the bandwidth. You have to multiply the bandwidth with a random number and you have to add that value with the old value, right? If you're, then after that, that same bounding corner bounding we have done now by using the lower bound and the upper bound. Same thing you can do here. After the pitch adjustment, right? Whenever you are improving the harmony, if this is new value, right, it is less than the lower bound, then you have to keep this value as the lower value, right? If the new value, whatever you are generating, this is greater than the upper bound, then you have to keep that value as the upper bound. So this part is for your bounding the solution with respect to your L and U value, right? Next, if you are not able to improve the harmony, right? So if your random number is greater than your HMCR, so you are using or you are generating the solution randomly by using the lower value and the upper value, right? Then what we are doing, you are updating the harmony by replacing the worst solution by the new solution. If new solution is better than the worst solution, right? Then you are incrementing the number of HMS vector, then until your maximum or the right, what you call that termination criteria is not reached, because you have to iterate for n number of iteration. You have to repeat same procedure. Then at the end, you have to produce the best solution or the best harmony as the optimal solution of the given problem. Right? So this is the same thing, whatever. So this is the basic steps you have to follow. Initialization, optimization problem, and the control parameters, whatever we have discussed. Initialization harmony memory, creating a new harmony vector, revising the harmony memory, right? Either you have to select from the HM or you have to select from the random. If you are selecting from here, you are doing the pitch adjustment. That's it. Then evaluate the termination criteria. So these 5 steps you have to follow to solve any problem using harmony search algorithm. Right? So this is a flow chart. If you relate these steps now, if you understood this algorithm or the procedure, same thing is represented graphically here. So you have to initialize the problems and the factors, right? I mean the parameters. Then you have to initialize the harmony memory randomly. Evaluate the fitness of the harmony. Then S equals to 1. S represents the number of iterations. Okay, and X equals to 1. So you can write it differently. This is the number of dimension. For every musical instrument, for every decision variable, you have to follow these steps, right? So what you are doing, you are generating a random number less than HMCR. If this is yes, you are considering the harmony memory, right? This is for considering from the harmony memory, right? Then what you are doing, we are doing the pitch adjustment. If R is less than PAR, then what you are doing, you are doing the pitch adjustment. So this is the formula for the pitch adjustment, okay? Next, if your R is not less than HMCR, then arbitrarily or the randomly you are selecting by using the lower bound and the upper bound. Then here you are choosing whether X is the n value. That means for the nth decision variables you have done this, then you have to come here. You have to revise the harmony memory. If you have not done, then you have to apply the same procedure for the next decision variable. That's why X is equal to X plus 1. Again, it will come back here, right? Now, after doing the pitch adjustment, right, again here you have to compare if X is less than equals to N, then, right, yes, then you have to, sorry, if X equals to 1 condition is there. If X equals to N, that means for all the decision variables you have updated, right? So you have to revise the harmony. Otherwise, again you have to go for the next decision variable. So here also you have to increment the value of X by 1. Again you have to come back here, right? So here, whenever you are doing for all the decision variables, you have to revise the harmony memory. Because when you get a harmony, right? Suppose 4 variables are there, x1, x2, x3. For x1, you are doing the same step. For x2, you are following the same. For x3 and x4. When you are getting the values of x1, x2, x3, x4, that is called a harmony only, right? By using these 4 values only, you can calculate the fitness value, right? So this is this upper part is for getting the new value of x1, x2, x3 and x4. Then you are revising the harmony memory. So where you are revising, if the new value, fitness value is less than the worst value. So this is written for your minimization problem, right? So what you have to do, you have to add this and remove the worst solution from the HM. Otherwise, you don't need to do anything. Same harmony memory will be there for the next iteration. So here you are combining whether you reach the maximum iteration. If you have not reached the maximum iteration, you have to follow the same steps for the next iteration. So we are incrementing the value of S by 1. Otherwise, if you have reached the maximum iteration, you are returning the best harmony from the solution. And that best harmony is the optimum solution of the given problem. Right, so this is the basic harmony search algorithm by using this basic processes, right? So you can solve any optimization problem. So let us see how it works for this sphere. So I will show you for only one iteration with all the possibilities, right? I will show for one R1 less than HMCR and one iteration for R1 greater than HMCR. So what we are trying to do here, right? So the same sphere function let us consider. So that is f of x equals to I equals to n to n xi square. We are trying to minimize. So this is the minimize. We are trying to minimize. Okay. So the lower bound is 0, upper bound is 10. And suppose the n value, number of decision variables are 4. So how to calculate the objective function? So the same problem we are solving for every problem, right? So for every optimization algorithm. So this is x1 square, x2 square plus x3 square plus x4 square. So this value we are trying to minimize. So there are 4 decision variables, x1, x2, x3 and x4, right? Now what will happen? Now we have to define all the parameters, right? So let us HSN, that is the sorry, HSMS, harmony memory size, right? Harmony memory size. This equals to 5. That means the population size equals to 5. So 5 initial solutions we have to generate randomly. And number of iterations, how many iterations you have to carry out, 10. So I will show you for 2 iterations only, right? So HMCR, suppose this is the 7, 0.7. PAR, this is 0.7, pitch adjustment, and the bandwidth is 0.2, right? So bandwidth also you can take in the range 0 to 1. Right? So these are we have initialized now. Next, what we have to do? We have to generate the random solutions, right, within the domain of the decision variable, and we have to calculate the objective function value, whatever we are doing in every algorithm. So this is the harmony matrix or harmony memory, you can call harmony memory HM. This is the harmony memory total. So in the harmony memory, there are 4 musical instruments: X1, X2, X3, X4, right? And these are the pitches of the sound produced by all the musical instruments, right, at a time. So these are the values. Suppose randomly whatever we have generated 2, 3, 0, 6 up to the last harmony 2, 3, 7, 5. So harmony means one solution. That is the mapping, right? So one harmony means the solution. That means the pitches of the sounds produced by different musical instruments at the same time. That is the meaning. Okay. So these are the 5 solutions of the 5 harmony we have generated randomly in the range 0 to 10. If you see, all the values are coming within that range, right? Next, you apply the fitness value, right? Your summation of xi square. If you add this one, how much you will get? Your 4 square plus, sorry, 4. 4 plus 9 plus 0 plus 36. So 36 plus 9, 45, 4, 49, right? 49 you are getting. Similarly, you calculate the same function, right? Summation of xi square, I equals to 1 to 4 here, right? So you will get 49, 162, 95, 125, 87. So these are the objective function values for the initial whatever solution or initial harmony you have generated, right? Next, what you have to do? I have to do the improvisation for every musical instrument, right? So first we have to find out this one, then this one, then this one, then this one. How you have to find out? We have to generate a random number r1 for this one, right? We have to improve this pitch, then we have to do for this, last we have to do for x4. Let us see what we are doing here. Suppose we are generating a random number, suppose 0.3, right? Suppose, so here also different procedure you can follow, right? So for every decision variable you can use the same random number, or for every decision variable you can generate a new random number. Both cases are possible. So for simplicity, for hand calculation, what I have done, I have used a random number, generate a random number, that is r1. This is same for all the decision variables. So these are 4 decision variables. So if you use different decision variable, different random number for different decision variable, you may get better solution also, right? So assume this R1 we are generating for all the 4 decision variables for doing the improvisation, right? So let us assume R equals to 0.3. So HMCR, what is the value we have considered? 0.7. So if you see here, your R1 is less than 0.7 because we have considered 0.3. That means we need to improvise the harmony by selecting one harmony from the HM, right? So what is the new harmony HSM new now? What is this value? How this value is coming now? See, for the X1, right? So 2, 4, 3, 5, I am considering the new harmony. So X1, X2, X3, X4. Now from where this 2 is coming? As R1 is less than HMCR, so you have to select any one value from the harmony memory. Now if you see, this is the values, possible values for X1 in the harmony memory. So any value you can consider. So 27302. Any value you can consider. So randomly you can consider any value, but out of this 5 solutions, right? So I have considered here 2 over. Next, same thing you have to do for X2. X2 you see for X2, these are the values 3, 3, 2, 4, 3. So which value you have considered? 4. That is randomly. Again for X3, you have to select one value from this, right? 0 to 1, because these are the pitches of the sounds produced by that musical instrument only, right? So maybe I have considered randomly as 3. For the next right? So these are the 5 values present: 6, 10, 9, 10, 5. So I have considered 5, right? So in this way, I am generating the new harmony as 2, 4, 3, 5 by selecting from the harmony memory only, because a random number whatever you are generating, that is less than your HMCR. Harmony memory considering red. Okay. Next, what you have to do, you have to, so whenever we are taking the harmony from the harmony memory, we can do the pitch adjustment, right? So how to do the pitch adjustment? Let us generate a random number, that is R2, this equals to 0.2 suppose. So this is less than PAR. So what is the PAR value we have considered? 0.5. So here your R2, this is less than your 0.5. So that means we have to do the pitch adjustment. And for the pitch adjustments, let us, what I am using here, if you remember the pitch adjustment, what we are doing, X new equals to X old plus minus you can use, right? So there is a random number you have to generate, and this is the bandwidth you have to consider, right? So what we have considered here, so simply, if you follow this equation, 1 minute. This is the equation, right? For hand calculation, what I have done here, simply I have considered R equals to 1 and bandwidth equals to 0.2, and I am using minus because I am trying to minimize this one, right? That's why R equals to 1. So generally in the range 0 to 1 you consider, but simplicity I have considered R equals to 1. So now you see, if you do the pitch adjustment, this 2 will be 1.8 because old value is 2 minus R value is 1, bandwidth is 0.2. So 2 minus 0.2 equals to 1.8, right? Similarly, the band here also you can do that, right? The random number you can generate differently for different decision variables. So for different decision variables also you can do the pitch adjustment differently. Right? For simplicity, I have used the same random number and same bandwidth for all the decision variables. Okay. So here, if you are using this equation and considering the value of R equals to 1 and bandwidth equals to 0.2, and I am subtracting, right? I am reducing the pitch. So I am getting this solution as 1.8, 3.8, 3, 2.8, I am getting 5, 4.8. Now you have to, what you have to do after doing the pitch adjustment, right? You have to compare this new solution with the worst solution in the harmony memory, right? If you see the harmony memory, just 1 minute. If you see the harmony memory, you see this red color, it represents the worst solution or the worst harmony in the harmony memory, because this is a minimization problem. So 162 is higher, right? So this is the worst solution in the harmony memory. So if the new solution is better than the worst solution, so we are replacing this one with the new solution. That means we are getting a new population there. So same thing here we are doing. So what we are doing, whatever the new we are generating, its fitness value is 48.56. Find out that one. Summation of I equals to 1 to n xi squared, right? So here you are getting 162, here we are getting 48. That means this is better. So you have to replace the worst solution with the new one, right? So at the end of the first iteration, now you see that's 162 is replaced by the new solution, whatever you got after the first iteration, right? So what we are doing, we are trying to avoid the worst solution in the solution space, right? And by using the pitch adjustment, there is a chance that we may get better solution for the subsequent iteration. So this is the first iteration over. So same thing you have to repeat, right? So this is the population now for the second iteration, and same thing you have to consider. You have to improvise the harmony, you have to adjust the pitch, right? Then you have to replace the worst with the new solution for this population also. So only I have shown you for this R1 less than HMCR, right? So another iteration I have here for this, if this R1 is greater than HMCR, what you have to do, right? So in the iteration 2, so this is the population you have to consider for the next iteration, right? So in the iteration 2, you suppose I am generating the random number 0.9. Again, I am generating for all the decision variables 0.9. So you can generate differently for different decision variables. So HMCR, if I remembered, we have taken 0.7. So R1 is greater than the HMCR value. So here we are not considering the HM, right? So what we are doing, we are selecting a random solution, right? So the random solution may be present in the HM also, right? Because we are following this constraint only, right? Whatever we are using, lower bound plus a random number into upper bound minus lower bound. So this will generate a random solution in the range lower bound and the upper bound. Right. So after that, in the basic HSA, pitch adjustment is not there. So I have not shown the pitch adjustment here also. We can go for the pitch adjustment here also, right? But here I have not shown the pitch adjustment. So let us, by using this lower bound, upper bound and this R4 value, I got the new harmony as 1524. Assume this is a selected random. Now your fx equals to, you calculate this one, 1 square plus 5 square plus 2 square plus 4 square. So 1 plus 25, 26 plus 29 plus 16. Something calculation difference. So 6, 20, 21, for 25, 46, correct. The 46, right? So if you see here, after the first population, which one is the worst solution? This is the worst solution. Whenever you are doing the second iteration, 125. That's why this is represented in red color. Okay. Now your new solution, whatever you are generating, that fitness value is 46. So this is better than 125. So what you have to do? So what is the output of the second iteration? So this thing has to be replaced by this new harmony with the fitness value is 46, right? So at the end of the second iteration, now you see we are replacing the worst harmony in the previous iteration 125 by this new solution, right? So always now what we are doing, you are trying to, right, avoiding the worst solution, because there is improvement in the worst solution every time we are changing the worst solution with the new solution. So there is a chance that that new solution also the best solution in the current harmony memory. If you see in this scenario, 46, that is also the best solution in the current scenario. Right? So with this, your second iteration over. So same procedure you have to follow until your termination condition is satisfied. Suppose after doing 10 number of iterations, our termination criteria is 10, right? And the number, I mean 10 times we have to repeat the procedure. We got this solution, right? So what is the output now? Suppose if this is the output for the 10th iteration, we are getting this one. So what is the solution here? So which one is the best harmony here? This is the best harmony in the harmony memory. So this is the optimal solution for that given problem, right? In this way, this is the basic harmonic search algorithm you can apply to solve any continuous objective function, right? By using these two intelligent operators. One is your improvising the memory. Second one is you have to adjust the pitch of the sound produced by every musical instrument, right? So this is the basic explanation of the harmonic search algorithm. If you have any doubt up to this, you please ask. Then I will go for this different improved version of this harmonic search algorithm, because there are so many parameters here, right? So how to properly tune those parameters, we'll see next. If any doubt up to this point? Okay, if no doubt is there, let us move towards what are the different control parameters in the harmonic search algorithm, right? We have seen there is the HMCR value is there, harmonic memory consideration rule, right? Or the rate, rule or rate. In some papers they are specifying rate, some papers that is rule is there. So you can use any terminology. So HMCR value, it will be always in the range 0 to 1, right? Next, pitch adjustment rate, PAR value, generally it is 0 to 0.5, whatever as per your literature, okay? Next, your harmony memory. Harmony memory also you have to define, right? That is the HMS value. How many number of solutions you have to generate, population size. Then your termination condition. How many number of iterations you have to solve the problem. These are the control parameters. So depending upon these parameters, there are different types of HSA, right? So one is your improved HSA, second one is your binary HSA, right? So there are different variation of HSA. Improved HSA is there, binary HSA is there, hybrid HSA is there, right? Then we will see some other types of HSA are there. So I'll give you a survey paper for this HSA. You can explore there. So whatever different types of HSA algorithms are there, all the algorithms are mentioned, right? So the references are given in that paper. So you can, if required, you can go through the different, right, different types of HSA from those papers. Right, whatever. With respect to that one, there is a bandwidth is there also, right? That's bandwidth, it is not given in this diagram. Bandwidth also you have considered. PAR, HMCR, BW bandwidth, harmony memory, termination criteria. So many researchers, they are trying to change this PAR, HMCR and the bandwidth value in every iteration, right? Like we have changed in the D, if you remember, right? Some of the control parameters, that mutation strategy, referential, your scaling factor, PC, adaptively we have changed in every iteration. So there are improved HSA where these values, bandwidth, HMCR and PAR, such as they are focusing to change in every iteration. So in every iteration, instead of using the same parameter, this parameter value you are tuning, right? So in the improved HSA, right? So the PAR, pitch adjustment rate, and the bandwidth, right? They are dynamically updated in every iteration. Iteration means in every generation, right? So these are the how to generate. For that, you want the pitch adjustment minimum value, you want the pitch adjustment maximum value. But in the range 0 to 1, give. Okay, or 0 to 1 or 0 to 0.5. This is the minimum and the maximum adjustment rates. PARGN means denotes the pitch adjustment rate in the current generation GN, right? So how this value will change, this PAR value will change in every iteration depending upon the PAR max, depending upon the PAR mean, depending upon the number of iterations and number of generation, right? So that formula is your mean value, PAR mean value plus the difference between the PAR max and the PAR mean divided by number of iterations. Suppose, right, you are doing for 20 iterations, so divided by 20 into, this is the current generation number. So every iteration what will happen, this PAR value will change. So there is a chance that, right, you may able to explore more solution space or more source space will be effectively explored. So this is one of the improved HSA where your PAR value we are going to change in every iteration, right? And the improved HSA also, the bandwidth value also you can change like the PAR value, because they are having effect on the pitch adjustment, right? So the bandwidth GN, similarly, bandwidth GN represents the distant bandwidth in generation GN. Okay. BW mean and the BW max, these are the minimum and the maximum bandwidth, right? So what you have to do, we have to set this mean and max value depending whatever the range is there. In that range you have to fix the mean and max, and within that mean and max you are going to change that bandwidth value in every iteration. Similarly, how the value will be changed in every iteration or every generation. So the bandwidth value in every generation will be the maximum value into exponential of, so this is the integer value of BW mean by BW max divided by number of iteration into current generation number. So in this way, if you do, the bandwidth will change in every iteration and you may able to explore effectively the solution space, right? And there is another, right, under the improved HSA, self-adaptive HSA is there. So this is the, here the bandwidth, this is formula is different. How the bandwidth is going to be changed in every iteration, right? So to capture the best solution for generating the new harmonies, self-adaptive HSA can be used where the bandwidth can be changed depending upon the iteration number, right? Now you see, if Ni is the total number of iteration and GN is the current iteration. Now, if you have to compare this one, if the current iteration is like in the initially, so we are 1 to 20 iteration you are doing, right? So during the first half of the iteration numbers, right? So the bandwidth will change differently, and in this part the bandwidth is changing differently. right? So in order to trade off, right, the balance between the exploration and the exploitation. So if Gn is less than Gn, the current generation is between this 1 to 20. So we have to update the bandwidth by using this equation. So bandwidth max minus difference between the max and mean divided by total number of iterations into 2 into current generation in this part. And in this part, what we are trying to do, we are trying to use the BW, right? So in this way, you can use you can modify the basic HSA algorithm into improved HSA, self-adaptive HSA, or you can combine both things, right? Combine means you have to do this one, this PAR adjustment along with the BW adjustment you can do, and you can see how it is behaving on a particular problem as compared to the basic algorithm. And there is another version of HSA is there, that is explorative HSA, where right the bandwidth changes with respect to the variation of the current population, or the standard deviation of the current population. So this explorative HSA means depending upon the standard deviation of the current population, we are changing the bandwidth, right? So we are using the population variance for modification of the solutions to the next iteration. So the distant bandwidth of the BW value was dynamically changed proportional to the standard deviation of the current population. Okay? So this will change with respect to the standard deviation. So this is the explorative HSA you can use to solve the problem also. Right? So there are different variants of HSA. Your improved HSA only I discussed. They are only right. Your self-adaptive you can use. You can update the PAR value. You can do the BW value, or explorative HSA you can use by using the standard deviation, right? So there are other versions are there. Your chaotic HSA there, how to handle the initial population, right? Chaotic map you can use. So you can explore further these HSA algorithms. Binary HSA is there for your feature selection or instance selection, right? When you want the binary values. So you can convert this basic HSA to the binary HSA also. There are multi-objective HSA also there. So more than one objective function how to handle. So I think we are having 2 sessions on multi-objective optimization. So Dr. Sujit Dasar is going to handle. So in that scenario, he will tell the concepts of multi-objective and how to find out the Pareto front of the multi-objective function. You can, after understanding those things, you can use the multi-objective HSA also. And there are different hybrid HSA also there, right? So you can hybridize this harmonic search algorithm along with other algorithms to get better solution for a particular problem, right? So there is right, there is different applications of HSA, right? Then you can apply in the engineering problems, right? Scheduling problems, machine learning can train the neural network, you can optimize the parameters of different machine learning models, different deep learning models, right? And different type of NP-hard combinatorial optimization problem also you can solve by using this harmony search algorithm, right? So these are the different applications with respect to different domain, right? So as the participants are from different background, right, different domain, you can see with respect to your problem, right, how the HSA are used, right? So this is only the breaks, the scheduling, right, which type of scheduling problems can be solved. And these are the different types of HSA, right? Whatever I told you, binary HSA, explorative HSA, right? Your adaptive HSA, improved HSA, D for dynamically HSA, different types of HSA they have used to solve the problem. So course time traveling, right? Flows of scheduling, your structural design of yes.
Okay, ma'am, sorry for interrupting. Is there any domain area for time series, please?
For 1 minute is there in the 1 minute. Let me check.
Okay, ma'am.
Some industrial engineering related something
Okay.
is there. You can see.
Yes, I already have. And for
No, industrial
electrical
engineering.
engineering, economic load dispatch,
Yes,
also time series related.
yes, that is there.
Yes.
Yes. Those are there, and different types of problems are there. So for different areas, these problems, right? Some problems has been solved by using HSA, different types of
Ma'am, this
HSA. As
paper
per your domain,
you could share with us, please, if you don't mind.
yeah. Yes, I will share, sir. I will share.
Thank
This
you
is a
very much.
review
Thank you
paper
very much.
only for
That's so,
2020. I will share.
thank you very much, ma'am. You're so
So
kind.
okay, sir. So civil engineering also, so many problems have been solved. Electrical engineering, right? Industrial engineering, clustering, networking, image processing, software engineering, mechanical engineering, photonics, healthcare, and these other different miscellaneous, right? So you can go for this paper I will share so that you can go through those papers. Then back reference is there, so you can get an idea how what are the problems and how they have formulated that problem to solve by using this HSA. Right? Different types of HSA they have used. And these are also different another applications also in the data mining, medical, agriculture, scheduling, power engineering, image processing, right? Astronomy, water resource management, different domain people have applied already. And what are the problems they have solved already? These are also written. I will share this paper so that you can see the problems, right? These are the basic only the domain is written. So what is the actual problem? If you go through these papers, if you read, then only you can understand what are the problems they have solved by using different types of HSA. Right. So this is all about your HSA algorithm. If you are having any doubt, you please ask. Otherwise, I will go to the MATLAB demo part for this HSA algorithm. Then we'll discuss the Firefly algorithm. Because the basic HSA algorithm is very simple, right? That is even very simple than your RAW algorithm also, right? But if you do the different, right, your improve the HSA, improvised HSA algorithm, you will get better solution. So, 1 minute. Yes. So this is the MATLAB code. I will share all the codes today only because today is my last session. So I will share whatever MATLAB codes or the Python codes I have discussed. Everything I will share today only, tonight. So this is the harmony. This is the improvised harmony search algorithm. This is not the basic HSA algorithm. So here the bandwidth, if I will show in this improvised harmony search algorithm, what we are changing here, we are changing these things, all things we are changing. We are changing the pitch adjustment rate as well as the bandwidth, right? So these two parameters we are changing in every iteration while whenever we are doing running, we are solving the problem by using the HSA algorithm, right? So the total runs 20 times we have to run the algorithm, like that you can fix number of variables equals to 3 precision variable. So these are the some right arrays you have to initialize. What is the best array memory or the best harmony now, right? What is the best fitness value? What is the lower bound? What is the higher bound, right? Low, high, n where index, right? So this program is written like that. So there is in the user prompt. So user has to give a choice, right? So there are different 5 functions are solved in this problem, right? I mean, we are discussing the sphere function, right? So this is the case 1 only. So the sphere function we'll see for the sphere function. Another 4, I think yesterday Dr. Priyanka ma'am, she has discussed about some Rosenbach function, right? That function is the case 2. Like that, different functions are there. So we'll see on the case 1 only. So that's why the default value also, otherwise I wrote for the spherical function only so that you can understand, right? So because we are discussing that sphere function every time, so you are habituated with that one, so you can see. So different functions, if you see the fitness function, you can see which function we are trying to minimize, all the minimization functions only, right? So we'll concentrate on the case 1 or that otherwise default condition only the sphere function we are trying to minimize, right? So okay, so this is the user prompt. So user has to give one choice. You have to choose only the function 1, right? Other function, if you are choosing, you have to understand what is that function. So how many times you have to run this HSA, right? So that is the total runs, right? Then this is the random number generator, reset the random number generator. Whenever you will use this one, every time you run the program, right? You will get a different random number generator. So it will generate different random numbers. Instead of generating the same random number, it will generate the different random numbers for each iteration. So now let us initialize the parameters. Your harmony memory size HMS, the population size, right? The maximum iterations. Then your pitch adjustment rate. So here I told you this is the improved harmonic rate. If you are using the basic harmonic rate, right, only you have to instead of using this PAR mean, PAR max, what you have to do, you have to set only the PAR value, right? Basic HSA. Similarly, let us discuss about the basic only, because right, the improved will be confusing for you, right? So let us assume HMCR PAR value we have considered 0.4, BW value this is 0.02, right? So so here we'll see the best harmony, whatever we are generating, that is the suppose best harmony we are initializing. Then this is a new candidate harmony vector. This NHCV, new candidate harmony vector, we are generating every time to improvise the harmony, right? Depending upon the random number and the HMCR value. So here the best fitness history, best fitness, right? Worst fitness item, all are we are initializing to 0. Next, suppose this is a HMCR, harmonic memory considering rule, that is the suppose 0.9 or 0.7, something you can initialize, right? Then this is the HM, you have to initialize the HM memory, right? So what you have to do here, for every, you have to iterate for the maximum number of iterations, right? So here this standard deviation, right, because there are different versions of the HSA algorithm, right? Here the standard deviations is used to generate the random solution, right? Along with the lower bound and the upper bound, along with the standard deviation of the solutions in the current population, we are generating the random, right? So you can omit this one to generate, you can also generate random solution by using low and high also. I mean lower bound and the upper bound also, right? That is the meaning. So here this is the, here it is the what is the minimum value and what is the maximum value. So these two statements, these are used in the improved HSA. So you can remove whenever you are running the basic HSA, right? Next, what you have to do, if you remember, for the all the variables, right? For I equals to 1, 2 number of variables in the problem, what you are doing, you have to generate a random number. And if that random number is less than your harmonic memory consideration rule or the consideration rate, right? What you have to do, we have to improvise the memory. So for that, what you have to do, you have to consider the memory, HM memory. From the harmony memory, you are selecting the value. That's why the temporary value you are selecting from this HM, any value you are selecting, but for with respect to that column only, right? Then the new value will be the temporary value. Then what you have to do, you have to do the pitch adjustment. For the pitch adjustment, again, you have to generate a random number. If this is less than the pitch adjustment rate, right? So what you have to do, you have to, right, depending upon the what you call, depending upon your bandwidth, right, and depending upon the current value, you have to update, right? So this is this one. So this one again, how to generate this one, whether you have to consider the standard deviation matrix or you have to consider the original HM matrix, depending upon that. So this part simply you can write, right? You can write that equation only if this random number is less than PSE. This equation only simply you can write the basic HSM, right? Temperature equal, or the temp equals to, or the new value equals to old value into, right? There's a random number plus or minus. I told you for the minimization you use minus always. So this is minus into the random number into the bandwidth value. Simply this equation will work, right? So here whatever is written, it depends again by using another variable, right? So this is the pitch adjustment rate, right? After doing the pitch adjustment, right? So if that else part is here, right? Else part, what you have to do, if this random number is not less than HMCR, so what you have to do, you have to generate randomly. That is the best, right? So random selection begins here. So I told you in the first two lines we have written the standard deviation, right? The standard deviation we are using from random solution generation. So what you have to do, so that step you can also eliminate. Simply we can write this one also by using that lower bound plus upper bound minus lower bound in the rand. That function simply you can route, or you can follow this one also, because this is the improved version. So if the standard deviation in the population is greater than 0.0001, this is the threshold, then you are considering from the low matrix, right? If this is the other condition, if this is not greater than 0.001, so you are considering the harmony matrix. That means this is the actual low and the high for the decision variables, and low HM and the high HM, it represents the low value in the harmony memory for that decision variable, and this is the high HM means high value for that decision variable in the harmony memory, right? So two different, either you are randomly whenever selecting, whether you are selecting between the lower bound or the upper bound, or the lower bound in the harmony memory or the upper bound in the harmony memory. For that, this is the thing. So this is the improved version, right? So now we have selected, right? We have improvised the harmony, or we have selected randomly depending upon the deviation in the population. Now what we have to do? We have to so this part this is for your dynamically adjustment of PAR and BW, right? So this is the improved version. So whatever 3-4 formulas I told you, you can use those things and you can go through that review paper so that you can explore different improved version of HSA also. If you are using the standard HSA, right? So this part you can remove here. Simply we find out what is the worst solution in the HA, right? Then what is the index? Then you compare. You have to compare the worst harmony with the current solution. So whichever is best, right? This is the if the current fit is less than the worst, then you have to, this is the less than means this is the minimization problem we are considering. So this is the better. So the worst solution you have to replace with the best new solution, right? Then what you have to do after the generation or after doing all the iterations, so whatever do, you have to find out the best solution. So the best you have to find out. This is the like you're right, which one is the best solution in an array. Like your programming, simply we are writing, we are assigning the first solution as the best, then we are comparing the first with the remaining solutions, right? So if you do this one simply through a for loop, then you will get the best index. So that will be the solution for your current problem, right? So this is the, right, you can display the parameter, what is the optimized value of those decision variables, and you can display the, what is the optimized function, right? Function value, I mean the value. So, so if you run this one, you can see the number of iterations, number of something, you can change here, enter your choice, it is asking, right? You see these are the different functions are there, spherical function, Rosenbrock, Bell's function, right? Different 5 functions are there. So we are discussing about only the spherical function, right? If you run this one minute. So if you see in every iteration, so how many iterations we have run the problem? 20 iteration, right? So what will happen here? If you see here, this is this something is wrong here. For that is a 0 also, it is calculating some value, right? That part I will correct and I will send you, because 1 minute, whenever it is getting 0 value, because that update part is there, for 0 value also it is showing some objective function value, but that is wrong calculation. I will check that objective function, somewhere some mistake is there. So if you run, you can understand how the objective value is changing, right, with every iteration for this sphere function by using this harmony search algorithm, right? So with this, if you use, you can use here your objective function, you can write in this user prompt function, and how to evaluate, right? How to evaluate that objective function, you can write here in one case. So this will work. Only it is unable to handle that 0 case. Somewhere some minor mistake is there, due to which it is unable to handle the 0. That I will check and I will send you, right? So this is all about your harmony search algorithm, right? Okay, I will share these codes. All the codes I will share. Just quickly let me discuss about the Firefly algorithm. So I am not going to give an example for the Firefly algorithm. Only I am going to discuss what are the intelligent operators we are using to intelligently handle the heuristic. Right? That I will tell only the Firefly algorithm. So as I told, Firefly algorithm, this is a bio-inspired meta-heuristic algorithm, and it is coming under your swarm intelligence, right? Like your ant colony, ABC, PSO, right? So this Firefly algorithm is coming under that category. So this was introduced in 2009 at Cambridge University by Yang et al. So how, which behavior is right mimicked in this optimization algorithm? So the algorithm is inspired by the flushing behavior of fireflies at night, right? How they are they're emitting some light, right? With this respect to the light, what happens? That phenomena is mathematically modeled by using this firefly algorithm. So what happens here? Any firefly, they can be attracted to any other brighter one. Whether is emitting a more brighter or more light, right? So other firefly will be attracted towards that firefly. So the brightness of a firefly, this is determined from the encoded objective function. So how will you define this firefly is bright or that firefly is bright? So that will be determined by using our objective function. Okay. So the brightness or the attractiveness, right? So this is directly proportional to the brightness. So the attractiveness between two fireflies is directly proportional to the brightness, but it decreases with distance. This is the law of physics, right? So that law of physics is also implemented here in the firefly algorithm. And the firefly will move towards the brighter one, right? And if there is no brighter one, what will happen? The firefly will move randomly, right? If it is getting a better, a brighter firefly, that firefly will move towards the brighter one. Otherwise, it will move randomly. Same thing in the optimization problem, right? If we are getting a new good solution, then we have to change that solution. Otherwise, we are changing that solution or replacing that solution with a random solution. Same concept in the optimization things. This firefly algorithm also, that is the firefly's behavior is mimicked in the firefly algorithm. Right? So, what are the characteristics of these fireflies? Generally, what happens? The fireflies, they have a flashlight, right? As a major characteristic. So, it can be used to attract the possible mates because attraction depends upon the amount of brightness. This can be also used to warn from the potential threats of the enemies. Right? So, the working of flashlight, it follows the physics rule. Your eye is inversely proportional to the distance between the two fireflies. That with the increase in distance, the flashlight intensity decreases according to the law of physics. So this thing we are using in the firefly algorithm, where R is the distance and this I is the intensity of light, right? So what happens when the firefly, they are blinking their flashlight, right? At the regular time instances, some reduction in that brightness will also happen. So those things are modeled in the some mathematical parameters, right? So whenever a firefly comes in neighborhood, they come together and form a couple. That means we have in the optimization problem, what we have to do, suppose a solution x1 is coming towards the solution x2. That means the x1 is changing its value with respect to x2 value. Right? So what are the equations we have to use here? So let me tell you the simple procedure here for the firefly. Right? So you have to start, you have to generate the initial population of fireflies because this is the swarm based intelligence. So you have to define the swarm size. So swarm size equals to 10 means population size equals to 10 or the number of fireflies equals to 10. Number of fireflies equals to 10. So 10 solutions you have to generate randomly. That is the meaning. Okay. Then what you have to do, you have to define the define and calculation of the objective function. It depends upon the problem. Suppose you are solving the sphere function, so you have to minimize xi square, I equals to 1 to n. Okay. Then you have to evaluate the attractiveness and the relative distance between each couple of fireflies. Right? So the distance here you can use by using the Euclidean distance. Okay, so the Euclidean distance can be used to find out the distance. Then the attractiveness also you have to find out depending upon the brightness or depending upon the objective function value between two fireflies. Then you have to update the firefly position. Like your particle sum optimization, you are changing the position, right? So first you are updating the velocity, then you are changing the position. Here, depending upon the attractiveness and the distance between two fireflies, you are updating the firefly position. Then what you are doing? You have to, right, you have to compare between the new firefly and the old, whichever is better, that you have to keep here, right? So calculation of new solutions and updation of light intensity. Then you have to find out the good firefly. That means that you have to give rank to the fireflies and you have to find the better solution than the previous one. If your termination criteria is reached, right, you have to end, and whatever best solution you are getting in that population, that is the solution of the optimization problem. Otherwise, again you have to repeat the procedure. So this is the basic procedure or the firefly algorithm, right? Same thing, the algorithm here you see, you generate the n initial solutions. I denotes the number of iteration, max iteration represents the iteration number, I is the intensity of brightness of flash. So you have to generate n solutions randomly. So for I equals to 1 to maximum number of iterations, what you have to do, you have to calculate the brightness. Then you have to arrange the fireflies as per the brightness. So you have to sort the I value such as Ij greater than equals to Ij minus 1. Right. So next you have to compare two fireflies with each other. Right. So for j equals to 1 to n minus 1 2, For k equals to j plus 1 to n2. For the next, suppose you are considering the first firefly, then you have to compare with the 2, 3, 4, 5. Right? Between every firefly, you have to compare. Then if Ik, intensity or the brightness of kth firefly is more than the brightness of the jth firefly, right? So we have to update the position of the jth firefly, because jth firefly will attract towards the kth firefly. So some mathematical equation we'll use here to update the values of the jth firefly, right? Then you have to, otherwise, right, if this condition is not satisfying, this one, right, if there is no better attractive firefly, so you have to move the firefly in the random manner. So you have to store the best solution at the end. So this is the steps, right? So this part I am not discussing now. Same thing it is there, right? So what is the mathematical equation? Let me tell this one. So generate a random solution. Suppose x1 to xn decision variables are there. Intensity means brightness means your objective value, right? So each firefly they will move towards the brighter firefly, right? So how to move that one? Now you see. So how to update the position of a firefly? So when you are updating the position of the firefly, suppose xi is there, xj is there. These are the two solutions. If this function, objective function of xi is better than objective function of xj, better. Suppose I am considering the minimization problem. If this is less than f of xj, so xi, so xj is less than xi. So xi will be attracted towards the xj. So xi will change its position. So how it will change the position? Same thing to say. If a firefly located at xj is more attractive than another firefly located at xi, so xi will be attracted towards the xj. That means the position of xi will move towards the position of xj. So how you have to do that one? So this is the intelligent operator we are using in the firefly algorithm, right? So xit plus 1 in the next iteration, what is the position of the firefly? This equals to its old position xit plus beta. Beta is the brightness factor into exponential of minus, right? Minus your gamma into r square ij. So r gamma is the absorption coefficient. Okay, absorption coefficient means because the fireflies they are continuously emitting lights, right? So we are assuming that some portion of light, right, this is absorbed. Like your ant colony optimization, we have used the evaporation constant, right? Similarly, this gamma, this represents the absorption coefficient. And r square ij, this is the distance, Euclidean distance between two fireflies. So exponential of this part into, right? This is the position of xj minus position of xi plus this is some randomness we are adding. So alpha t is the randomization parameter. This delta t, this is also a random number, right? This is a randomization parameter. Delta also, this is a random number. And this gamma is the absorption coefficient. So this intelligent operation of the expression you can use to update the position of a firefly, right? So these are some of the basic values of this alpha we have considered. How to initialize the your randomization parameter initially in the range delta will be 0 to 1, and you can use this formula to find out, or alpha value in the range 0 to 1 also you can fix some value, right? Beta is the control parameter for attractiveness, and always finally whatever I don't know, I have gone through 5-6 papers, everywhere they have used the value of beta equals to 1. So you can see, right, what the other possible values of beta, so that you are getting this good solution for a particular problem, right? So this thing already I told you, right? This is the algorithm. You have to follow this algorithm. Then you have to perform the greedy selection, generate random solution, compute the intensity of the light or the brightness. Then you have to update the firefly with position. You have to update the position by using this one. This equation already we have discussed, right? Then you have to perform the greedy selection. Greedy selection means whether the xi at the tth iteration, whatever it is there, and the xi at the t plus 1, whichever is better, right? Whichever is better, that you have to consider for the next population. So xi t plus 1 and xi t, which is better, that will be considered for the next generation, right? So you have to repeat this process, right? This one, you have to repeat this process until your termination criteria is fulfilled. Otherwise, termination criteria is fulfilled means you have to exit. Sorry, if your termination criteria is not fulfilled, you have to repeat this test. And at the end, right? So all the fireflies you are storing. Suppose population size equals to 5. F1, firefly 1, firefly 2, firefly 5. So you are getting these values, right? This is the position, and this is the objective value or the lightness or the brightness of that firefly. So suppose this is 10, 5, last is suppose 2. As this is a minimization problem, at the end if you are getting this solution, right? So which one is the best solution? This fifth firefly, because having objective value is 2, and this is a minimization problem. So this is the optimum solution for the given problem. Right? So this is the basic firefly algorithm. Again, there are different improvised version of the firefly algorithm also, right? Because we are having different parameters here, whatever we have seen: population size and the swarm size and the number of fireflies, attractive constant beta, absorption coefficient gamma, maximum number of iteration, randomness string alpha, randomness, right, reduction delta, right? These are the different parameters. So properly tuning of these parameters, there are other hybrid or the improvised firefly algorithms also there. Again, I will share one review paper or the survey paper so that you can see what are the different types of firefly algorithms available, in which domain people have also used. Okay. Now say, now you have studied so many optimization algorithms, right? Now I will change these parameters and you have to tell this intelligent operator is similar to which algorithm, how it's similar to other algorithms, right? Now this is the simple equation we are using in the firefly algorithm. Position we are updating for the ith firefly. This is the old position. This is the attractive constant. Okay. This is the what we are considering the absorption coefficient along with the distance. This is the difference between the position of the jth firefly and the ith firefly, and this is some randomness we are giving. This is nothing. This is only for giving some randomness to the solution. That's it, right? Now you see movement of, you see the equation carefully. 1 minute. Right. Now you see the movement of fireflies depends only on random walk when beta equals to 0. Why it comes to the random walk? Can anybody tell me? If beta equals to 0, why the firefly, there is a random movement for the firefly? Why? If this beta equals to 0, what will happen? This term, second term will be 0, right? Beta is multiplied with that one. So that second term will be 0. So what is the equation now? The intelligent equation is your xi it plus 1 equal to xi plus this one. Because this is the randomness, this is his original position. So randomly it will move, right? That's why if the beta value, the attractive constant parameter equals to 0, so the fireflies will move randomly, right? And the this is the absorption coefficient gamma. This is a mean factor of convergence speed, right? That is the its value you can take in the range 0 to infinity. And if you consider 0 value, what will happen? If you consider infinity value, what will happen? We'll see in the next slide. Okay. So generally, this gamma value for many optimization problems, right? People are using this 0.1 to 10, right? So you have to properly tune these parameters also, how it is affecting on a particular problem. So you have seen there is a alpha is a randomization parameter, beta is the attractiveness constant or factor, and gamma is the absorption coefficient. Now we'll see, we have changed the beta value, we have seen beta equals to 0. So there is, this value will be 0. So there is the random walk for a particular firefly. Now you see, depending upon this gamma value, how the fireflies will behave. Now you see, if gamma equals to 0, right, what will happen? If gamma equals to 0, yes, if this gamma equals to 0, right, so e to the power 0, it will be 1 only. So this part will be 1. Okay, so what it will come? Xi t plus 1 equal to xi t plus beta into xj minus xi plus alpha t. So can anybody can tell me it corresponds to which algorithm, whatever optimization algorithms we have discussed so far? If this absorption coefficient equals to 0, this term is going to be 1, right? So we are getting the intelligent operator as like this. So this is which algorithm, which is mimicking which algorithm? We have studied so many optimization algorithms, right? Which algorithm you have studied? You please verify this one, right? If gamma equals to 0, it is mimicking which algorithm? And if this is the gamma equals to 0, right? If this gamma equals to infinity, right? So what will happen if gamma equals to infinity? Now this second term will be 0. Second term will be 0. This part will be 0, right? This part will be 0 means this total part will be 0. So again there is a random movement, right? That means xit plus 1. This equals to xit plus 0. Second term is 0. So this is alpha t delta t. So this is mimicking which algorithm? This is mimicking which algorithm? Random walk, where you have considered the random walk, random movement, random solution, in which algorithm you are considering? Have you remembered, right? Random walk we are considering in the simulated annealing algorithm, right? And the difference between the positions we are considering in the PSO. Yesterday only, right? Yesterday only we have discussed the particular sum optimization by Priyanka madam, right? How the displacement is the position between the two solutions we are considering, right? So these are the two variations. If absorption coefficient equals to 0, so the Firefly algorithm, this is become a special variant of your particle sum optimization algorithm, right? And your absorption coefficient is infinity, right? So this is the parallel simulated annealing algorithm. Why parallel simulated annealing algorithm? Can anybody explain? What do you mean by parallel simulated annealing here? So we have seen in the simulated annealing algorithm, we are considering one solution. This is not the population-based algorithm, right? We are considering one solution. We are trying to explore the neighboring of this solution, right? But here, whenever the Firefly algorithm, your absorption coefficient is infinity, right? Why we are calling parallel simulated annealing algorithm? Because this is a population-based algorithm. For every solution, right, we are trying to explore its solution. For this solution, we are trying to explore the neighbor. For this solution also, we are trying to explore its neighbor. For this also, we are trying to explore its neighbor. For this solution also, we are trying to explore. That's why this will become the parallel simulated annealing algorithm if your absorption coefficient is infinity. That is the difference between the depending upon the absorption coefficient, right? So in order to avoid towards the PSO or the simulated annealing algorithm, this gamma value also you have to properly tune. And generally it is written in the 0 to 1 also you can take, right? So in the different improved version, right, whatever parameters we have discussed, there are different mathematical formula to change these values in every iteration. Like we have seen in the HSA, right, how to properly tune these parameters in every generation. So there are different variations of this Firefly algorithm where you can change this attractive constant every iteration, this absorption coefficient, as well as this alpha and delta value also you can change. So you can go through the paper, the reference that is already there, so you can download that paper, otherwise I will forward you that paper so that you can understand, right, how this improved version of Firefly algorithm works, right? So these are the different traditional Firefly algorithm. These are the modified. Whatever we have discussed only the traditional Firefly algorithm. So these are the different modified algorithms are there in that paper. References are there. You can go. These are the hybrid Firefly algorithm, right? How other, right, you see the genetic algorithm, differential evolution, neural network we have not considered. This ant colony, how they are integrated with this Firefly algorithm to perform a or to generate the hybrid Firefly algorithm. Okay. Next, again, this Firefly algorithm, there are different applications of this Firefly algorithm. You can see different types of engineering problem with respect to your noisy objective function, dynamic objective function, multi-objective, right? So building problems. Now the classification, this is generally all the problems related to your feature selection and instance selection, right? Those type of problems you can solve by using this Firefly algorithm under classification. And different types of engineering problems, similarly in right, image processing, antenna designing, industrial optimization, right? This industrial optimization you can see somebody asked, I think, the robotics, semantic way, wireless network, business, right? In the financial, somebody you are asking so many things, so you can go through these things. chemical engineering, civil engineering, right? These are the different engineering optimization problems where Firefly algorithm people have used, right? And they got good result also. So you have to verify what type of problems they have solved, right? So these are the 2-3 references I have followed. So whatever PPT I have prepared as for this, mainly with this article along with some other papers I have prepared. So you can go through this systematic review on harmonic search algorithm, theory, literature and applications. So in this paper, all types of HSA are given with their back references, right? And for this Firefly algorithm, you can see this comprehensive review of Firefly algorithm, swarm and evolutionary computation, and the systematic review on Firefly algorithm, past, present, and the future archives of computational methods in engineering. You can see this one. This is the paper title. This one. This is the computational method. Okay. So this is all about your harmonic search and the Firefly algorithm. Just 1 minute. I have some MATLAB code for this Firefly algorithm also. But that is again, that is the improved Firefly algorithm. That is not the basic Firefly algorithm, right? So let me close this one. Okay. So this Firefly algorithm, this has been written for this. Only here the alpha coefficient we have seen, right? Randomness, providing randomness to the position of a Firefly. Only that alpha value has been changed in every iteration. Okay, we'll not consider that one. We'll see the basic things only, right? So what is the variable size? How many variables, right? What is the variable size? Mean, what is the lower bound? What is the upper bound? How many iterations? This is the Firefly algorithm parameters. Maximum number of iterations, population size, swarm size. This is the gamma, beta, alpha. So this alpha value, we are going to change this one. Okay. Delta, right? This is the m equals to 2. This is for calculating the distance because we are using the Euclidean distance, right? So Euclidean distance, for that m is used for taking the power 2, right? So this is for now. If this is scalar value, right, then you have to consider simply the difference divided by square root. Otherwise, we have to find out the Euclidean distance. This is the norm function for finding the Euclidean distance. To find out that r values, r square is that value. Okay. So initially you create the empty your Firefly position, Firefly cluster, okay, empty Firefly structure you consider. Then you have to initialize the population array, right? Then what you have to do for all the Fireflies or the population size, you have to create the initial Fireflies, right? So this is for creating the initial population. Right? If you read, you can understand these things, right? Because so many algorithms you are discussing, right, with code. So you can, better it is good to write. You have to write your code by yourself so that it is you can understand. Because understanding others' code is very difficult, right? If you write by yourself, it will be easy for you. Then you have to hold the best cost value because this is our solution at the last after the termination criteria is reached, right? So inside this loop, what you have to do, right? If you have to do that randomly you have generated the population, right? Next, what you have to do for j equals to 1 to n population, you are comparing the brightness of between every pair of fireflies. That only we are doing. That's why two loops are there here, right? So for I equals to n to population, for j equals to n population. So you are comparing between every two fireflies, right? If that is whichever is better, right? If because this is a minimization problem, since sphere function we are solving, this is a minimization problem. Whichever is smaller for that. So this part is for updating the brightness of that firefly. Already I told you that formula, like old position plus that is the attractive. Sorry, brightness factor beta into that exponential of minus r square ij, right? And into multiplied by the difference between the position of the two fireflies for some constant, right? Randomness. So you can use right there. Then if bounding is required, you can do the bounding also because bounding step I have not written in that algorithm. So you can do the bounding. If by updating the position, right, this is satisfying. This is not satisfying the upper and the lower bound constraint. So you have to do the bounding. So this is the bounding. Then what you have to do? You have to compare that new solution. Whenever you are generating a new position, you have to compare that one with the old value. So whichever is better, that you have to keep. So this part represents that one, right? So in this way, if you run this part for displaying only the which iteration, what is the mutation, right? What is the objective value? And here at the last part, if you see, this is the improved version of the Firefly algorithm. So the alpha value only it is changing in every iteration. The randomness factor it is changing in every iteration. Right? So here the cost function is also the objective function is sphere, I think. Cost function is sphere only. So the same sphere function that is minimizing xi square is I equals to 1 to xi square sum of, right? So, 1 minute. So how many iterations are there for this? Okay, let me run. So you can see how the objective, right, function is changing here. You can see, I think iteration 100, iteration 100. You can see from by iteration to iteration, so it's how the objective function is changing because this is a minimization problem, right? So 4.9508 into 10 to the power minus 5. This is coming, right? So this is close to 0 only, right? So in this way, you can use the Firefly algorithm and you can explore the other types of Firefly algorithm along with the hybrid Firefly algorithm, right? So that you have any optimization problem in respect to your domain, you can solve those problems. With this, right? And it's all about your harmonic search algorithm and the Firefly algorithm. So this is from my side. If you are having any doubt, any questions, you please ask.
Ma'am, excuse me, would you please be kind to repeat that hybrid portion once again to us, please?
Which algorithm? Hybrid portion of which algorithm, sir?
I mean, hybrid Firefly algorithm or hybrid, I mean, harmonic search algorithm,
Hy-
or how we combine both, I mean, harmonic search as well as this Firefly to create the new hybrid algorithm.
you want to hybridize Firefly algorithm and the
Yeah.
harmonic search
Yes.
algorithm? Yeah, okay. That
Yes,
that
ma'am.
part you have to see. That paper you can refer, sir. You can understand which part you have to do the hybridization, right? Hybridization you can whenever you are applying that intelligent operator, there you have to do some changes, right? Because hybrid optimization algorithm we have not discussed so far, right? So I will share one paper where your hybridization of ABC with D is there. I will share, sir. You can refer that paper and you can understand how to hybridize this HSA with Firefly algorithm. I will share
Okay.
that hybridization of ABC with D or hybridization of ant colony with G. Also, some papers are there. You can go through this
Okay.
hybridization optimization methods.
So those
Then you can
papers, ma'am,
apply.
I mean, are available in this review
Yes, yes,
article?
no. The hybrid models are not there in the review article. Some hybrid
Okay.
models are there here. Here in this, you will get some hybrid models with respect to
But
HSA only.
basically, where I can have those hybrid models and as well as the raw, I mean, codes for MATLAB or in Python.
Yeah. We'll give, sir. We'll share everything. We'll share. We'll share.
Okay.
Some hybrid models you will get in this paper also, sir. This past, present, and
Okay.
future systematic review and Firefly
So
algorithm.
these two
Uh,
papers only, ma'am. These two papers only we should.
Yes. These three papers somewhere there,
There
sir.
is, I mean, nothing else apart from these two.
No, you have to see that back reference. You have to see, sir, because some reference paper they have given. I will share these papers so that you can see their references. What reference papers they have followed, you can understand from there. Some of the hybrid models are there.
Okay. So, ma'am, I mean, you will be kind to share those papers with us, right, ma'am?
Yes. I will share tonight. I will
Okay,
share
great.
everything.
Great,
Okay.
great, ma'am.
Okay.
So, ma'am,
Okay.
from where actually I can also find out the codes about those hybrid
Code,
algorithms?
sir.
Uh,
You
yes,
will not
please.
get any code from anywhere, right? You have to write your code, sir. Whenever you are
Okay.
hybridizing, you have to write your code.
So,
It's
ma'am, I
better
mean,
to
for
write
teaching
your code.
purposes, I guess for teaching purposes, you
Uh,
already have built up some codes. I,
this
I
is
I I wish it will be available on the hybrid portion as well. So would you please be
okay.
kind to share those codes with us so that we could study those codes to build up our version of codes, please?
So far I don't have any hybrid code, sir. If I will write the hybrid codes, I will say, sir. So far I don't have any hybrid code.
Okay, ma'am. So my humble request to you is that I will actually try to write down my hybrid code, and I will
Yeah,
try to
yeah.
communicate with you through email. Would you please be kind to put me some light on that so that I
Yes,
could
yes.
be in your touch to learn much more from you? Thank you very much.
Yeah, sure, sir. Sure, sir.
Thank you very much, ma'am. Thank you very much.
Is any other queries? Any other questions? The chat box, anything is there? Yes, yes. Somebody asked, can we use this HSA for selecting a features? Yes, you can go for binary HSA. You can use binary HSA for feature selection. Okay. If no questions are there, so I will stop here. So next session we will start at 5:05.
Thank you very much, ma'am, for your excellent lecture for us. Thank you very much. And I will be I will definitely try to be in your touch through email and WhatsApp. Would you please be kind to share your
Okay.
email address and
Yeah.
with us, please?
1 minute, sir. I'm sharing. Yeah.
Thank you very much, ma'am. Thank you very much.
Okay. Okay. Thank you all. So we'll start our next session at 5:05.
Okay, ma'am. Okay, ma'am.
Good evening, everyone. Welcome to the second session of day 6. So, in this session, we have Dr. Sibram Paningarahi. So, I welcome you, sir. So, sir will discuss about the whale optimization and its application to deep learning based time series forecasting. So, before Dr. Sibram will start this session, let me introduce him. So Dr. Panigrahi is currently working as an assistant professor in the Department of Computer Science Engineering at Sambalpur University Institute of Information Technology, Odisha. He has completed his MTech and PhD in Computer Science Engineering from BSSUT Burla, Odisha. He has completed his BTech in CSE from Biju Patnaik University of Technology, Odisha. He has been sanctioned with 5 research grants from major funding agencies of India, like Science and Engineering Research Board, that is SERB, Indian Council for Medical Research, ICMR, Odisha State Higher Education Council, and Sambalpur University and Hindalco. Recently, he has developed and deployed an electricity load forecasting software employing a deep learning model for India's one of the major power distribution company, Tata Power Western Odisha Limited Distribution Limited, that is called as TPWODL, through his research project sponsored by OS HEC. He has also published many papers, more than 40 research articles in various reputed journals and conferences. His research interests include swarm evolutionary algorithm, machine learning, deep learning, artificial intelligence, and time series forecasting. He has served as a reviewer of more than 30 reputed international journals and conference of various reputed publishers. He has delivered various several talks in various organizations, in seminars, symposiums, webinars, and faculty development program, workshops in various National Institute of Importance also. He is a senior member of IEEE and presently working on developing crude oil price forecasting methodology employing deep learning model through his project sponsored by SERB, Government of India. Apart from research, he also teach various subjects. He loves to teach and deliver various talks in various organizations. And he also loves to learn from the audience by discussing any research topics and technical topics. So with this introduction, I request Dr. Paningrai to start the session. Sir, it is over to you. I think your voice is not audible. No, your voice is not audible. Other participant can respond.
The voice is not audible.
Okay, okay. Same here. Yeah. Please take your time.
Now is it audible?
Yeah. Now it is audible.
Okay, thank you, Sanjay sir, for the nice introduction, and thank you for the opportunity for interacting with some nice audience and academicians across India and across globe. Without making much delay, let me share my screen. My screen is visible. My screen is visible.
Yes, sir. Yes, sir. It is visible, sir.
Okay. Okay. So the context of the thing is it is a faculty developing program on optimization technique theory
Sivaram
method
sir, your voice
emerging
is little bit low for me.
little.
Other audience can also say
Okay.
if they are getting the same thing.
Okay. Now is it audible?
Still, your voice is low, sir. Can you increase the
Okay.
volume of your system if possible?
Okay. No, I it's maximum. Okay.
Okay.
Okay. Can I continue? I will try to speak in a louder voice so that it will be audible. Is it fine?
Other participant can respond.
Other participants can respond. Is it fine? Okay. So
Okay,
as
proceed.
the okay context of the faculty development program is on optimization techniques, theory, and emerging applications. So I have divided my talk into two parts. One is I will discuss one optimization technique, that is fuel optimization technique, fuel optimization algorithm, and I will apply it and other swarm and evolutionary algorithms for time series forecasting using deep learning models. Okay, so in this presentation I will first go through the theory part of well optimization algorithm, then I will go through the well optimization variants, applications, and its hybridizations, then I will go through the MATLAB implementation, then I will go through the application part. First I will go through time series forecasting, then time series forecasting employing deep learning, how it can be done, then how time series forecasting can be done by employing meta-heuristic algorithm optimized deep learning models. Then I will go through hybrid time series forecasting methods using statistical and deep learning models and using meta-heuristic algorithms in that. Then I will go through fuzzy time series forecasting models using deep learning model and meta-heuristic algorithms. Then if time permits, I will go through training deep learning models using meta-heuristic algorithms. Then I will go through some Python and MATLAB implementations. So let us first go through well optimization algorithm. In 2016, Mirzali and Lewis proposed one of the simplest and promising nature-inspired meta-heuristic algorithm known as well optimization algorithm. The well optimization algorithm actually, as all of you know that whether the algorithms are either swarm-based algorithms or evolutionary algorithms, or it mimics some features from the nature. So this well optimization algorithm is basically a nature inspired meta heuristic algorithm which mimics the social behavior of humpback whales. So social behavior means it doesn't capture every detail of the humpback whales. Rather, it loosely couples the hunting behavior of humpback whales with optimization. So as we are trying to mimic the humpback whales, so let us first have some idea regarding whales, then we will go through how we can mimic the social behavior of humpback whales for optimization. So basically the whales are the fancy creatures and they are one of the most biggest creatures till day or nowadays. They are approximately, a grown up whale is approximately 30-meter long and weighs 180 tons. And the whales never sleep. Why they don't sleep? Because they can't breathe from the water. They have to jump or go outside water and they have to breathe. So they never sleep. They are highly intelligent animals with emotions. They can communicate with each other. And the most important thing is they have spindle cells like humans. And in fact, they have 2 times more spindle cells than humans. The spindle cells are usually responsible for judgment, emotions, and social behaviors. So we can't say that whales are more intelligent than humans, but males has intelligent capability like humans. And coming to their social behavior, some type of whales live in groups and some type of whales live alone. But here we are concerning regarding the group behavior of whales. So there are various kinds of whales. Out of them, some are killer whales, some are minke whales, some are sea whales, and the most important type is humpback whales. Why? Because of their intelligent characteristics. Because they have 2 times more spindle cells than other kind of whales. And another one is right whales, finback whales, and blue whales. So here we will concentrate on humpback whales. So let us go through how the humpback whales do their social behavior. So the humpback whales go 15-meter down. So this is according to Mary Jolly, the proposer of whale optimization algorithm. He has written in his paper that the humpback whales go approximately 12-meter down the water and then start to create bubbles in a spiral space shape around the prey and swim upward the surface and try to kill the or try to eat the school of fishes. So the whales usually eat the small fishes. So here you can see that these are the small fishes. Okay. So first the whales do what? They go search for this school of fishes, or usually called as prey. So first they search the prey, then they go 12-meter to 20-meter down the water level, then they do a spiral circular shape and they move upward by bubbling. So the bubbling will help in attracting the school of small fishes so that they can we get around at that, and the whale will do what? It can trap the school of fishes, then it can eat them. So we have to model this behavior of whale. So first one is what? First they need to find the prey, search for prey. So here the whales live either in a group or in a or alone. So here we are considering the whales in a group. So the whales will do what? First they will search for the prey. So which whale will get the or get nearer to the prey, then other whales will follow them, right? So how we will mathematically model this process of eating the school of fishes by the whales. So let us go through the mathematical model for this one. Basically 3 steps are involved. The first step is search for prey. First they will search the prey or the school of fishes. Then what they will do? They will encircle the prey. Then they will go 12-meter down the prey and they try to do a spiral bubble net feeding behavior, and they will try to eat those school of fishes. So now let us see how this behavior we can map mathematically. So first one is encircling the prey. So humpback whales can recognize the location of the prey and encircle them. But since the position of the optimal design or the optimal position of the prey is not known a priori, the whale algorithm assumes the current best candidate solution is the target prey. It means what? There are certain set of whales. There are certain set of whales, whale number 1, whale number 2, whale number 3. Then each whale represent a candidate solution. Now what we will do, its whale means the position of whale represent a candidate solution. Now what we will do, out of a group of whales, the whale having best fitness or best fitness value, we will consider as the location of the prey, right? So after the best search agent is defined, the other search agents will hence try to update their position towards the best search agent. So in the encircling prey, what they do, a group of whales will move for the prey, then the whales which are nearer to the prey, it means the whales having the best fitness towards that whale, all other whales try to move. So how will we model it? So here you see, here I hope all of you have studied differential evolution and particle swarm optimization. In that also you have seen that we are taking a base vector. So let it is x, or if I am writing x best, it means that this is the best vector. So x best plus f into xr1 minus xr2. This is nothing but your DE best 1 right? DE best one mutation scheme. Similar to this, what we are doing over here, you see, we are generating the next xit plus 1 by taking x best and subtracting a into d. A is a constant where d is the difference vector. So how we are computing the difference vector? The difference vector is nothing but a c constant x best minus xit. So here, if we will compare it with the DE best one, this is nothing but, so xt plus 1 is nothing but xt best minus a into, in place of d, if I will put this one, what I will get, c into x best minus xit. Okay, so in differential evolution, what
Hello,
we are doing,
sir.
we are yes sir.
Hello.
Yes.
So,
Yes.
sorry to interrupting, but here actually T is for the iteration.
T is for the iteration. T is for
Okay,
the
okay. Thank you
iteration.
very much, sir. Please carry on.
Yeah.
Okay, sir.
Okay. So xt best minus. So here we are doing a plus, but here we are doing a minus. Okay. So it's not a problem if the difference vector becomes a negative value. It will again become plus. And here also, if the difference vector becomes positive negative, it will become minus. So it's almost identical, right? So next, here the constants a and c are updated randomly, and you see in the recent well optimization problem papers, what they have done, they have developed self adaptive well optimization algorithm, where what I have done, they have identified the value of a and c based on the problem in hand. So this is whole about the encircling the prey. So here you just remember that this is equation number 2.1 in the base paper. Okay, so encircling the prey is the equation number 1. Next, so how, what actually they are doing? So if I will go for a 2D visualization, if this is the x best, so in a two-dimensional space, you can see that x best have two components. One is x, another one is y. So here x star represents the best value of x and y star represents the best value of y. Now, if this is the position of a whale and this is another whale, let's say z, so it will try to move towards this best whale. So best whale means if I am doing the x component subtraction, so x component subtraction will do what? X star minus x means this will move towards this side. And if I am updating the y component of this space or of this point, then I am trying to move this direction. So I will go towards the best solution, right? Next, if I will go for a 3D visualization of this one, so here you see, if this is the best current best well position, and this is the current position of another well, then if we are trying to move this well towards best well, then what it will do, you see, x star minus x. So if I am subtracting the x component of current well from the x component of the best well, then I will move towards this direction. Similarly, if I will subtract the y component of current well from the best component of this well, then I will move this direction, right? Similarly, if I am subtracting the z component, I will move in this direction. So I am trying to move from towards the best solution, right? So similarly, it can be thought of to a n-dimensional space. I
Sir,
have just
hello.
shown you from the base paper how into the
Sir,
yes.
sorry again for interrupting, but in
Yes,
this
sir.
mid position, I mean, how we are getting assured that this is our, I mean, optimal position?
No, I am assuming that. I am assuming that this is the optimal position. If this is the optimal position, and if this is a current position of a particular search agent or whale, then if we are trying to move towards the best position, if I am doing this x best plus x best minus xi, then you see from the x base or towards the x base, I or to the x best, I am adding a difference vector. It means I am going towards the best solution, right? So basically we can say that here we are doing exploitation. Exploitation means we are searching around the best solution to get a better solution, right? Is that clear, sir?
Would you please be kind to repeat this
Okay.
last line, please?
Okay. So here what we are trying to do in the encircling prey, we are trying to move towards the best solution. It means what? Around the best solution, we are trying to search another solution. So we are searching around the best solution. It means we are doing exploitation. Means around the we are searching at the local region of the best solution. This is called as exploitation. So encircling prey, in encircling prey, we are doing one kind of exploitation. Is that clear, sir? Okay. So next one is the spiral bubble net feeding. So here you see how the humpback whales catch the school of fishes or catch the prey. They go a 12 meters down the water level, then they follow a circular path and they move upwards and they catch the prey and they eat the prey, right? So here you see there are two things. One is they have to move in a circular path, and you see the diameter of the circle is reducing. The diameter of the circle is reducing, right? So the circular path diameter should reduce and they have to move towards the up. So in order to capture these two things mathematically, what they have done, as I have told you previously in the encircling of prey, they are doing x based minus r into some difference vector. So what they will do, they will move towards the best solution. Okay, means they will move upward or they will move towards the source of prey. And the second one is what they will do, they have to follow a circular path, and that circular path should reduce its diameter. So in order to achieve this, what they do two kind of things. One is from x star t minus a into d, means they are subtracting a difference vector from the best solution. And the second one is what they are doing, d dash into cos 2 pi l. So all of you know that cos 2 pi l means it follows a circular path around the best solution. So at some time with a probability of 50% they are moving upwards, and with a probability of 50% they are following a circular path. So what they are doing, the whale is actually moving
Sir,
in
sir,
a
sir,
circular
sir,
path.
sorry for interrupting.
Hi.
Sir, sorry for interrupting. Would you
Yes.
please be kind to repeat the first condition once again?
Okay, sir, here you see the whale should move towards the prey. This is the first condition. And second one is it should follow a circular path. Okay, and the diameter of the
Okay.
circular path should reduce. So the first one is it should move towards the prey. Towards the prey means prey, we are considering that the location of the whale with best position is called as the location of the prey. So for the first one, it is moving towards the best whale, that is x star t minus a into d. And second one is it should follow a circular path. It should follow a circular path means, you see, we are doing cos 2 pi l. So where L is a constant again, and L value will reduce from 2 to 0. It will reduce with a constant constant value. Okay. So the diameter will again reduce. So you see, if we will add these two things, first it will move towards the prey. Second thing, its concentric circle should reduce. If we will add these two things, or sometimes if we will follow this one and sometimes if we will follow this one, then we will follow a circular path whose diameter is reducing and still we are moving towards the prey. Is that clear, sir? So here, like this, we are modeling the spiral bubble net feeding thing. So here you see again we are moving towards the best solution. So it means what? We are doing exploitation. So this is also one kind of exploitation. So now you see always searching around the best solution is not good. Because why? You see, let me show you. Suppose we are having n number of variables. Variable 1, variable 2, variable 3, variable n. And suppose this is our sort space. Okay. Now in swarm and evolutionary algorithms or in nature inspired meta-heuristic algorithms like well optimization, what we will do, we will start with a set of solutions. Let my solutions are like this. This one. So each solution represents a candidate solution to the problem. And let me take this one and take this one. Now you see here what is the best solution. Suppose it is a minimization problem. I think this is the best solution, right? So if all other wells or all other chromosomes or all other search agents will move towards the best solution. So where they will move? They will move around it. Okay. So if they will move around it, what is the best solution that I will get? I will get trapped to this solution. Is that clear? So you see, it is not the global best, it is a local best solution, right? But where is the global best? Here is the global best solution. So you see, if we are moving always towards the best solution, it is not, we know that we will get faster convergence. Quickly we will converge. But the problem is what? The chances are there that we will trap to a local optima. So what we will do in order to have exploration means we have to source the other spaces of the source space. It is wiser to move towards a random solution. So this you have already studied in DE rand. So in DE rand, what you have done it like this: xt plus 1 equal to xt plus or x rand plus f into xr2 minus xr3, right? So here it does more exploration. So motivated from this, what they have done in the search for prey, they have done exploration of the search space. So in the exploration of search space, what they have done, you see xt plus 1 equal to xt rand. Here you see the base vector is a random vector. So random vector means what? In the first two phases, that is in the encircling of prey and spiral bubble net feeding behavior, what we are doing? We are moving towards the best solution. So there we are doing exploitation. But here what we are doing? We are doing exploration because we are moving towards a random solution, right? So now random solution plus A is a constant, D is a difference vector, right? So in search for prey, we are moving towards a random solution. So now you see the usage of both best and random solution balances between exploration and exploitation. So it means what? If our random initial solution is like this, and if this is the search space, so sometimes what we will do, we will move towards the best solution. So here, what was the best solution? Let me take it over here. So now here you see in this, the best solution, if it is a minimization problem, this is the best solution, right? So what we will do, if some of our wells or some of our search agents or if some of our chromosomes will move towards the best solution, it means we will search around the best solution, means we will get to here, we will get to here. So the best chance is there, we will trap to here. But you see, this is again a local optima, right? But now if some of our agents will move towards the best solution and if some of our agents will move towards a random solution, so now you see, if we are fortunate enough and if the random solution is this one, and if we will search around it, so we may go to here, we may go to here, and the chances are there that we will reach the global optima. right? So we have to balance between exploration and exploitation. So moving towards the best solution gives what? Faster convergence. But the problem is you may trap to a local optima. But moving towards random solution means it will take huge amount of time to converge. But the chances to trapping to global optima is more. So DE based, so as you have already studied, DE based, we are doing exploitation, whereas DE rand, we are doing exploration. Whereas you see in well optimization algorithm, in two phases, it do exploitation, and in this phase, in the search for prey, it do exploration. So it tries to balance between exploration and exploitation. All of you are clear regarding this? Any doubt, dear participants? I want to hear from you. Any doubt?
So far we're not finding actually any kind of doubt.
Okay, thank you. Okay. So next one is the algorithm. So this is same to all other swarm and evolutionary algorithms. So first what we will do, we will initialize the parameters. Initialize the parameters means the algorithmic parameters such as A, C, I, and P. Then generate the random initial solution. Random initial solution means if there are D decision variables, then and if the population size is 20, then we have to generate 20 solutions randomly. So initial solutions are always random because it is a stochastic search method. Next one is evaluate the fitness of each search agent. So if we have generated 20 random solutions, we will evaluate the fitness of 20 random solutions. Then determine the best search agent. Out of 20 search agents, what is the best search agent? Or we can say that what is the best well position, right? Next, initialize the iteration counter. So we will repeat it for certain set of iterations. So next, for each search agent, what we will do, we will update the A, I, C, I, and P. These are the algorithmic parameters. Then we will check if P is less than 0.5. Then we will apply two things. One is equation 1, another one is equation 8. Equation 1 is what? Equation 1 is nothing but encircling the prey. Encircling the prey. And equation 8 is nothing but search for prey. Search for prey. So you see, with a probability of 50%, we are doing two things. With a probability of 50%, we are doing either encircling of prey or search for prey. So here you see again, we are dividing it for two times. So we can say that 25% chances are there for encircling of prey and 25% chances are there for search for prey. So here you see encircling of prey, we are doing exploitation, and search for prey, we are doing exploration. Now, if P is less than, if P is greater than 0.5, then we are using equation 5. Equation 5 is nothing but your bubble net feeding behavior, which is nothing but, which is again a exploitation phase. So you see here 75% we are doing exploitation and 25% we are doing exploration. So this is in the traditional well optimization algorithm. It means what? In the traditional well optimization algorithm, it doesn't balance the exploration and exploitation. So it does more exploitation. Does more exploitation means faster convergence. But it does less exploration means what? It may trap to local optimas, right? So in order to avoid this, recently the authors have tried to improve the exploration capability of well optimization algorithm. Even we have done one work and we have submitted it. I will tell you what we have done to improve the exploration. So in order to improve the exploration, what we have done, I will tell you. So instead of taking the best solution, so best, if we will move around the best solution, then what we are doing? We are doing exploitation. But if we will do a group based solution, group based means what? We will randomly select 5, suppose the group size is 5, we will randomly select 5 search agents, then we will take the best out of it. So you see, here we have taken randomly 5 solutions, so exploration is there, and we are taking the best out of the 5, so we are doing a exploitation. So we have incorporated both exploration and exploitation while choosing the best solution. So this is one way you might approach in well optimization algorithm. The next one is, this is the pseudocode of the well optimization algorithm, what I have told you just before the flowchart. This is the pseudocode. Initialize the well population, then calculate the fitness of each search agent. Let X star is the best search agent. Then while the number of iterations is not reached, it may be anything. Okay, here the author have considered the number of iteration as the termination criteria, but you may also consider rate of change of best solution. So rate of change of best solution is what? The best t minus 1 by best t. If the fitness of best t minus 1 is not changing quickly as best t, then also you may stop, right? There are various stopping criteria that I think previously have been discussed. You can apply it over here also. Next, for each search agent, you will update the algorithmic parameters, and if p is less than 0.5, means with 50% probability, we will use encircling of prey and your search for prey, and with 50% probability, we will do bubble net feeding behavior. And again, this 50% will be divided into two parts, 25% and 25%. Right? Next, after doing this, so here you can see that we are using 3 mutation schemes. But here we are not using any crossover scheme. We are only using mutation schemes, right? So instead of using a single mutation scheme, here the authors have used 3 mutation schemes. Next, check if the search agent goes beyond the search space. If it is beyond the range, the decision variables, then we have to update it again. Then calculate the fitness of each search agent, then update the best solution, then increment the counter, and you will repeat this process until the termination criteria is satisfied. When the termination criteria is satisfied, we will use the best solution as the solution to the problem. So now we will go through the MATLAB code of it's not GW, it should be well optimization algorithm WA. Okay, so this MATLAB code is freely available. You can go through this link and you can find the MATLAB code of this one. So will I discuss the MATLAB code or I will move forward? Dear participants, will I discuss the MATLAB code or I will move forward?
Please be kind to discuss the MATLAB code.
Okay, thank you. Okay, let me show you the MATLAB code. Okay. So here you see, this is the main function. So here first we are initializing the number of search agents. Then you see, as it is a stochastic algorithm, what I have done, I have repeated for certain number of times. Means stochastic algorithm means what? If you will run that algorithm once, and if you will run it again, the answers will be different because the initial solutions are randomly taken. So the final solution after the termination criteria may differ. So it's always better when you are using swarm and evolutionary algorithms, repeat the experiments for at least 20 times and apply statistical tests like Wilcoxon signed rank test and Friedman-Neyman hypothesis test to derive decisive conclusions, right? Next, maximum iteration I have taken as 50. Next, here what we are doing, we are trying to optimize 23 benchmark functions. So I have written a for loop and I have executed it from 1 to 23. So 1 denotes function number 1, 2 denotes function number 2, like this. Okay. Next, I will repeat this much for number of iterations. So this much will be executed once, and once the result will be computed, then again it will be repeated. Similarly, it will be repeated for 10 number of times. Here I have taken number of repetitions as 10. Next, here I am getting the function details. then the upper bound, lower bound, and objective function of the functions. Then I am calling the well optimization algorithm. Well optimization algorithm, what I am passing? I am passing the number of search agents, then maximum iteration, lower bound of that particular problem, upper bound of that particular problem, dimension means number of decision variables in that problem, and the objective function of that problem. So let me go through the well optimization algorithm. So here you see this is the function. So I will return the leader score. Leader score means best solutions fitness. Leader position means best solutions decision variable values. Then convergence curve means the fitness in each iteration. So here what I will take, you see the search agents max iteration, this I have taken. Next, initially the leader position is all zeros initially, and the leader score is infinite. Why I have set to infinite? Because as it is a minimization problem, initially I am keeping it to infinite. So whatever the next value, it will be less than infinite. So it will be updated accordingly. So if it is a maximization problem, what you have to do? You have to take the leader score as minus infinite. Then I have to initialize the population or position. So position I have initialized randomly from the upper bound and lower bound. Okay, so lower bound plus upper bound minus lower bound into rand. So it will give you what? It will give you a set of values from a uniform distribution within the lower bound and upper bound. Then here I have taken the convergence curve. So in every iteration I will have a best chromosomes or best whales fitness that I will store in the convergence curve. Then this is the whale optimization algorithm. While t less than max iteration, what I am doing? First I am obtaining the upper bound and lower bound flags. Means if a position is beyond the upper bound and lower bound, then I am getting that and I am setting it. If it is more than upper bound, I am setting the value to upper bound, and if it is less than the lower bound, then I am setting it to the lower bound. Then the fitness of each search agent is obtained. Then if the fitness of the search agent is less than the leader score, so you see this is a minimization problem. So your leader will have the least fitness. So if fitness is less than the leader score, then what I will do? The leader score equal to fitness, means I am assigning the fitness to the leader score, and I am assigning the position of that search agent as the leader position, because it is a minimization problem, right? But if it is a maximization problem, you have to set it as greater than. So here instead of less than, you have to keep greater than. Just this much. Next, what you have to do? I have got the parameters, algorithmic parameters. A, you see, as I have told you, it decreases randomly from 2 to 0. Okay, sorry, it decreases linearly from 2 to 0. Next, similarly, A2 also decreases linearly from -1 to 2. Then for each search agent, I am generating two random numbers, R1 and R2, and I am obtaining the value of A and C. All the algorithmic parameter values I am obtaining. Then what I am doing, you see, if P is less than 0.5, P is a what? P is a random number. Okay, random number from a uniform distribution between 0 to 1. So if P is less than 0.5, then I have to do what? Encircling of prey and search for prey. Then again I am checking whether absolute value of A is less than 1, then I am doing encircling of prey, and if absolute value of A is greater than 1, then I am doing search for prey. So you see, encircling of prey has a chance 25% to occur, and your searching for prey will have a 25% chance to occur. Now if P is greater than 0.5, then what we will do? We will go for the bubble net feeding behavior. So you see, this is the bubble net feeding equation, that is equation 2.5. You see this code, I have taken it from Mirijali site, whatever reference or whatever link I have provided, you can also download it and you can use it, right? Next, I have incremented the iteration counter, and convergence value I have stored in the convergence curve array. Then I am just printing the T and leader score. T means iteration counter and leader score is fitness of the best well, right? So I hope all of you have understood it. Is that clear? May I proceed? Dear participants? Dear participants, have you understood? Okay. Next, let me go through some of the advantage and disadvantage of, sorry again, here instead of GWO, it should be WOA, well optimization algorithm. So this advantage and disadvantage I have collected from this paper. So here you see combining with different algorithms is incredibly comfortable. A good convergence rate. Why a good convergence rate? Because you see 75% we are doing exploitation and 20% doing exploration. So the convergence rate is good. Rapid discovery of good solutions because we are doing more exploitation. Appropriate for various types of optimization problem. Efficient for global search approach. Appropriate for both continuous and discrete space. Storing strong neighborhood search property. And these are some of the advantages. But disadvantage, you see, I have told you this one, may result in premature convergence. Why may result in premature convergence? Because 75% we are doing exploitation, right? And the next important thing is too many parameter tuning. You see, in DE, we are just tuning two parameters. One is F scale factor and the crossover probability CR. Whereas here we are tuning 5 parameters, right? Next, go through the various variants of GWOA. So again, it should be WOA. So it has been applied to continuous problems and binary problems. It has been applied in fuzzy domain and crisp domain. So what I have discussed right now is a single objective problem, whereas it has already applied to multi-objective problems. So in the improved version of well optimization algorithm, chaotic behavior have been incorporated, Levy-Flight equation have been used. Opposition based learning means what? If we are taking one side of a set, then what is the opposite side of a solution of that one? So both are compared and the best candidate solution is used for the replacement. Next, it has been used for the hybridization with other meta-heuristic algorithms like PSO, local search, Gray-Wolf optimizer, colliding body optimization, memetic, simulated annealing, Moth-Flame optimization, and other algorithms. And it has been used to optimize the parameters of artificial neural network. And in the application part, what I will do, instead of artificial neural network, I will go for the deep learning models. How you can optimize the parameters of deep learning model by using swarm and evolutionary algorithms, I will discuss. And it has also been used for determining the parameters of support vector machine. So now let us go through some of the applications of GWO. So this again I have taken from this. Yes.
What is Levy-Flight? Levy-Flight.
Sir, Levy-Flight is an equation which is used. It is I haven't remembered the equation, but it is an equation which is used to improve the exploration capability of a particular algorithm, right? So it has been also used in WOA, well optimization algorithm.
Okay, sir.
Okay. Next, you see this paper is from 2019. You see, by 2019, this is a survey paper published in Swarm and Evolutionary Computation. Okay, I didn't find any recent survey. That's why I have referred to this one. You see, by 2019, it has been applied in various areas in electrical engineering, civil engineering, in classification problems, clustering problems, image processing, mechanical engineering, control engineering, networks, industrial engineering, task scheduling. I think Sanjay sir is working on this area, right? And some other areas also, right? So now let us go through the application part. So the first part is looking at the perspective of this FDP. The first part is theory, practice, and application. So I have discussed one theoretical meta-heuristic algorithms like well optimization algorithm. Now I will go for the application part. In the application, first I will go through time series forecasting, which is my research area, and time series forecasting using deep learning. Then how time series forecasting we are doing by using meta-heuristic algorithm optimized deep learning models. Then we will go through hybrid time series forecasting methods using both statistical and deep learning models, and whose parameters are optimized by using meta-heuristic algorithms. Then we will go through contrasting to those crisp time series forecasting methods. I will go through fuzzy time series forecasting methods, and I will tell you how fuzzy time series forecasting is done by using deep learning, and how meta-heuristic algorithms play a big role in fuzzy time series forecasting using deep learning. Then if time permits, I will go through training deep learning using meta-heuristic algorithms, and I will bet you that today we are not using meta-heuristic algorithms for training deep learning models, but after 5 to 10 years, we are definitely going to use meta-heuristic algorithms to train the deep learning models. So whether we will develop it or somebody else will develop it. Then finally, I will go through some Python and MATLAB implementation of these things. So let us
Hello,
go through what
sir.
yes,
So would you please be kind to go to
yes,
the previous slide, please?
okay. This one?
So previous slide. Yes, this one.
This one. Okay, yes, sir.
Okay, okay. Sir, no, sir. Previous slide, please. Previous slide.
Okay, previous. Okay, this one.
Yes,
This
this
one?
one.
Oh, yes.
Uh,
Yes.
yes, sir. This one. So this, I mean, optimization algorithm. It is being used for time series forecasting as well.
No, in this survey, it hasn't been used, but I have personally used well optimization algorithm for time series forecasting.
Okay. So
Here
basically,
I
sir,
haven't mentioned.
I'm not an engineer, but I'm actually
Okay.
from the field of management, and I'm working in the field of financial engineering. So that's it will be
Okay.
great for me if you please be kind to show details about that this gray whale, optimization algorithm, its application for multiple time series orchestration. Thank you very much, sir.
Okay, definitely. I will show you one code using MATLAB also. How how well optimization algorithm will be used for time series forecasting. Okay.
Okay, sir. Thank you very much, sir.
Okay. Okay. So let us go through what exactly a time series is. A time series is a set of observations of the same variable measured sequentially through time. It means what? Suppose we want to measure the temperature. 5 days ago, we have measured the temperature. Next day, we have measured the temperature. Next day, we have measured the temperature. So if we are measuring the temperature in a time interval, then it becomes a time series. So now you see, in this internet and IoT era, all the data are measured through time series. So we are going to get a huge amount of large scale time series in future. In future, what? Right now also we are getting a huge amount of large scale time series. So these time series forecasting techniques need to be studied thoroughly so that we can get some very practical application of it. So what thoroughly? I will tell you, I am practically benefited from it. I have got the 5 projects, all are based on time series forecasting. Okay, so let us go through how time series forecasting we will do. So a time series is a set of observation of the same variable measured sequentially through time. So this X can be anything. It may be temperature, it may be a stock value, it may be a crude oil price, it may be temperature, it may be bath temperature, pot temperature. Pot temperature means where the aluminiums are produced from bauxite, or where the materials are produced from the minerals. And it may be number of passengers traveling in a train, number of passengers traveling in a aeroplane, number of students taking admission, number of persons working in a call center, number of call volumes, and amount of internet traffic. So whatever we are measuring through time, it's nothing but a time series. So now what are the components of time series? Or there are basically, if I will go for the classification of time series is of two types. One is discrete valued, another one is continuous valued. Discrete valued means if we are measuring the time series at regular time interval or a discrete interval of time, then we are calling it as a discrete time series. But if we are measuring the time series continuously through time, for example, your heart rate, it is a continuous time series, right? But if I will to take price of mango, so it is a discrete time series. So anyway, the continuous time series can be converted to discrete by random sampling or by taking average at regular interval of time. And another classification of time series is time series may be crisp or may be fuzzy. For example, if I am measuring the temperature, if temperature is today's temperature is 20 degree, tomorrow's is 23, tomorrow next day is 25, 28, 30, 40. So you see, if it is a real number, then it's a crisp time series. But instead of this, if I will tell that too hot, too cold, low, high, medium, if I will use linguistic terms, then it is called as a fuzzy time series. Now, the crisp domain can be converted to fuzzy domain and by using a technique called as fuzzification. And from fuzzy domain, we can convert it into a crisp domain so that we can get a crisp value. And that technique is called as defuzzification. Okay, so you see all the things we are doing in a crisp domain. But what we can do, we can convert it into fuzzy. We can work by using the fuzzy logic techniques. Then again, we can take it back to the crisp domain by using defuzzification, and we can operate on that. We will go through all the things in detail. Okay. So the next one is, what are the components of time series? The time series has basically four components. One is trend, seasonal, cyclical, and irregular. So let us see what exactly a trend is. So a trend is a pattern in data that shows the movement of a series to relatively higher or lower values over a longer period of time. Here the important term is higher or lower value over a longer period of time. So you see, if I will give you one example, you see number of passengers traveling in a airline. You see it, if it is from 1960 and let us say it is to 1990. So you see the number of passengers in every year, it is increasing, right? So it is gradually increasing. So it is having an increasing trend. Or what you can have, if the number of childs dying every year, if you will take, you see it is having a decreasing trend. So what is a trend? Trend is either increasing or decreasing gradually over a longer period of time. This is one of the component of time series. The next component is seasonality. Seasonality, as its name suggests, seasonality means seasonal effects. Okay, if I will take the mango price, what is the mango price? Mango price in summer is low, whereas mango price in other time period is high. If I will take the temperature, temperature in daytime is high, whereas temperature in night time is low. Temperature in winter is low, whereas temperature in summer is high. So if your time series is affected by these values, by the seasonal values, then that is called as seasonal pattern, or that is called as seasonality, right? And usually seasonality may be yearly or weekly, monthly, quarterly, or it may be hourly. If you see, if I will say the internet traffic, it is high during your working hours, as well as it is high up to 12 o'clock or 1 o'clock, 1 a.m., 12 a.m. or 1 a.m. And after that, during the night time, it might be low. And it can be also measured in hourly what? It is 15 minutes or 1 minute. It can be anything, right? Next one is cyclical component. So cyclical component, you see, it is similar to the seasonal components, means it is a repeating pattern. But you see, in here, the cyclicity or the repetition should be greater than 2 years. If it is more than 2 years, then we will not term it as seasonal, we will term it as cyclical, right? And the fourth component is irregular. Irregular means these are the components which cannot be predicted, right? So no matter how efficient we are, how accurate we are, we cannot be 100% accurate every time. right? There will be some component that cannot be predicted with 100% accuracy. So this irregular component cannot be predicted, right? So next one, it by knowing the components of time series, let us go through what exactly time series forecasting is. So time series forecasting is the process of predicting the future outcomes of a phenomena by systematically analyzing the past observations. For example, suppose we have observed a time series x1 to xn, and if we want to predict xn plus h by analyzing x1 to xn, then it is called as time series forecasting, right? So you see, we are doing time series forecasting every day. We are doing time series forecasting whether tomorrow we are going to take the umbrella while going to the college or not. Yes, tomorrow there might be rain, so let us take the umbrella. Whether tomorrow I am going to come to my home or not for taking the lunch, that also we are predicting. Whether tomorrow there will be a cyclone or not, that also we are predicting. Yes, we are predicting every day. How we are predicting? By our past knowledge and experience. Similarly, in time series forecasting, the future values are predicted by analyzing the past observations. So here you see, here I have written xn plus h. N plus h is the forecasting horizon. Forecasting horizon. So now you see, if h is 1, it means xn plus 1 we will predict. So this is called as one step ahead forecasting. When h is greater than 1, that is, it is called as multi-step ahead forecasting. So suppose I want to predict x5 by analyzing x1 to xn, then it is called as multi-step ahead forecasting. And you see, multi-step ahead forecasting is crucial than single step ahead forecasting. At the same time, multi-step ahead forecasting is challenging than single step ahead forecasting. So how will you do multi-step ahead forecasting? You see, sir, by using x1 to xn, we can predict xn plus 1. Then what we will do? We will use x1 to xn plus 1. Then we will predict xn plus 2. Then by using xn plus x1 to xn plus 2, we will predict xn plus 3. Similarly, we will go on predicting xn plus 5. So this is called as recursive or repeated one step ahead forecasting for multiple step ahead forecasting. This is one type. And another one is by taking x1 to xn, we will not predict these intermediate ones. We will directly predict x5. This is called as direct multi-step ahead forecasting. I will go through single multi-step ahead forecasting, and if time permits, I will also go through multi-step ahead forecasting. Okay, next one is forecasting method. So forecasting method is a procedure to predict the future values by systematically analyzing the past observations. So there are basically three kinds of forecasting methods. One is judgmental, univariate, and multivariate. Judgmental means we are forecasting by using our own judgment. If tomorrow there is going to be rain or not. If we are using our past experience to predict it, then this is called as judgmental. Whereas univariate forecasting methods use only a single time series. If we want to predict whether tomorrow there is going to be rain or not, and if we are using past rain data, yesterday how much rain, next day how much rain, next yesterday how much rain, if we are using only rain data, then that is called as univariate forecasting. Whereas multivariate forecasting uses what? Here, if we want to predict the rain, and if we are using rain time series, we are using humidity time series, we are using temperature time series for predicting the rain time series, then that is called as multivariate time series. But today I will fix to univariate time series forecasting. So where univariate time series forecasting is important, when the predictor variables are not easier to identify, there univariate time series forecasting is preferred over multivariate time series forecasting. Now, what is a forecasting model? Forecasting model is a tool to reveal the relationship existing in the past data and using which the future values are predicted. So there are basically two kinds of forecasting models. One is statistical, like ARIMA, autoregressive integrated moving average, exponential smoothing, your theta, naive. So many statistical GARC statistical models are there. But nowadays, the machine learning and especially the deep learning models are extensively used for time series forecasting. Now you see how we will use the machine learning models for time series forecasting. Before that, let me tell you why statistical models are not used. The statistical models assumes the linear relationship between the past values and the future values. However, most of the time series are nonlinear in nature and suffer by temporal and spatial variability. Temporal means based on time, we will have some nonlinear characteristics. So the statistical models do not provide better forecasts when the time series becomes nonlinear. And nowadays, the real world time series are highly nonlinear. So machine learning models has the capability to capture the nonlinearity. So nowadays, machine learning models are widely used, although statistical models are also used in conjunction with machine learning models, but widely machine learning models are used. So let us see machine learning, or as the time series are going to be longer or large scale. So instead of machine learning, the deep learning models are more suitable to capture the underlying patterns existing in the time series data. So let us see how deep learning models can be used for time series forecasting. So here you see, suppose we have observed a time series x1 to xn and we want to predict xn plus 1. And let me take a model. So due to lack of space, I have just taken a 3-layer neural network. So it can be up to any number of layers, right? And let me assume that the future value depends on past 3 values. So here I will take x1, x2, x3 as input and x4 as the target. Next, what I will do, I will slide the window. Then I will take x2, x3, x4 as the input and x5 as the target. So similarly, you see, if I will slide the window, then what we will have, I will have the input target pattern. X1, x2, x3 is the input and x4 is the target. Then x2, x3, x4 is the input and x5 is the target. Then x3, x4, x5 is the input, x6 is the target, right? So by using this input and target patterns, what I will do, I will obtain the model parameters. Model parameters means the weights and bias components of the neural network. So once the model parameters are obtained, then what I will do, I will give xn minus 2, xn minus 1 and xn as input. Then what value I will get? I will get the xn plus 1 value. That is the future value. So this is how the deep learning models are used for time series forecasting. So now here the big question is what? How many number of inputs? So sir, you have assumed three inputs, but how you have got those 3 inputs? How many number of layers? Sir, you have taken 3 layers, but how many? It is 2, 3, 10, 20, 100. Now it is 1000 layers are even possible to train. So how many number of layers? How many number of neurons in each layer? Sir, you have taken 2 neurons in the hidden layer, 1 neuron is the output layer. But how many layers? If the number of layers are 100, then in which layer, how many number of neurons? Then the important thing is activation function. So whether you will use ReLU activation function or sigmoid activation function or CeLU activation function or LU activation function or 10H activation function, which activation function you will use, how to choose. Then which kernel initializer? Sir, what is the initial weights of the neural network? How will you choose? Whether you will use Glorot initializer or Hay initializer or Hay initializers from a uniform distribution or normal distribution, which one to use? Which optimizer? Whether you will use Adam optimizer or you will use RMS prop or you will use AdaGrad or you will use Ada Delta. Which one to use? What is the batch size? Means after how many number of inputs you will update the weights. What is the learning rate? Now what is the deep learning model? Whether you will use LSTM or you will use GRU or you will use convolutional LSTM or you will use by LSTM or you will use by GRU. Sir, so many questions. How to get it? And the only answer is your meta-heuristic algorithms. That is one way. Now another way is grid search. But grid search is not so efficient than your meta-heuristic algorithms. It is not so flexible like your meta-heuristic algorithms. So what I will do, I will tell you how to do time series forecasting by using normal deep learning. Then I will tell you how will you do time series forecasting by using swarm and evolutionary algorithm optimized deep learning. And I will tell you that this thing right now we are submitting a paper, but still I am sharing it because this is the future, right? So you see, for time series forecasting using deep learning, first what you have to do, the number of significant inputs, K, of the deep learning model. Can you hear me?
Yes, sir.
So just a minute. I think I am having some problem. Okay. Okay. First, the number of significant inputs K of the deep learning model will be determined by analyzing the autocorrelation and partial autocorrelation function of the series. But you see, the problem is autocorrelation and partial autocorrelation function only captures the linear relationship in the data. So identifying the number of inputs by using autocorrelation and partial autocorrelation is not so ideal. But still, the authors are using. Then the time series will be pre-processed. Pre-processed means normalized. Normalized means they will be converted to a range between 0 to 1 or -1 to 1. Then treatment of trend components. So I have told you a time series, in a time series it may have a gradual increasing or gradual decreasing trend. So how will you convert this increasing and decreasing trend? How will you tackle it? So one method is called as differencing. Suppose you see the time series is 1, 3, 5, 7, 9. It is an increasing trend. Now you see how will I convert it into a, or how will I eliminate that trend? By simply doing fast differencing. So fast differencing, 3 minus 1 is 2. 5 minus 3 is 2. 7 minus 5 is 2. 9 minus 7 is 2. So now you see this is the transformed series. And you see in this series there is no trend. So what you can do, if your time series has trend, you have to treat it. Then if it has seasonal components, you have to do seasonal treatment. How will you do seasonal treatment? By subtracting the seasonal average from the time series. Next, the time series of length n will be transferred to n minus k pattern. So time series, it is a single set of values. So you have to convert it to input and target pattern by using the sliding window technique. So what I have shown you, the sliding window, right? So you have converted the time series to a input and target patterns. Then you will split the input and target patterns into 3 parts: train, validation, and test. Then by using the train and validation, you will obtain the deep learning model parameters. Then by using the test set, you will evaluate which deep learning model is better and which architecture is better, right? But this is the traditional way. Okay, I will tell you how to optimize. Next, once the forecasts are obtained, you have to denormalize. Denormalize means you have converted it into 0 to 1. So you have to take it back to its original scale. Detrend, if you have done the treatment of trend, you have done the reverse. You have to do the reverse process. Then you have to deseasonalize, and then you can obtain the true forecast. Then once the true forecasts are obtained, you can measure the accuracy by using the actual time series and the forecasted time series. But now, here in this slide I haven't addressed how to know the parameters, means how many neurons, how many layers, what is the activation function, what is the optimizer, what is the batch size, what is the learning rate, how to do it. So now you see, for this we can use swarm and evolutionary algorithms to optimize the deep learning model parameters, and this is the current trend and current application. Okay, so first you have to take the time series, then you have to pre-process it, means you have to normalize the time series and you have to treat the trend components. Similarly, here you can also treat the seasonal components. Okay, if seasonality is there, then you have to transform the time series into input and target patterns. Then you have to split it into train, validation, and test set. Then the important thing comes, you have to encode the deep learning topology into a chromosome of the swarm and evolutionary algorithms. Okay, or if I will tell well optimization algorithm, you have to encode that deep learning topology or deep learning architecture into the position of the well. So how will you do it? So here you see, this is one of the chromosome of chromosome, denoting the deep learning architecture. So now you see here what I have done, the first gene or the first variable represents the number of neurons in the first layer. And the second one is activation function. So you see activation function may be ReLU activation function, maybe it may be sigmoid activation function, it may be bipolar sigmoid activation function, it may be CELU activation function, it may be leaky ReLU activation function. So you see number of neurons, it is a real number, let's say 15. So the number of neurons will be 15. Activation function, it's let's say 3. So 1, we are denoting 0 for ReLU, 1 for CELU, 2 for sigmoid, and 3 for LU, right? So if it is 3, we will randomly initialize it. So it will represent the LU activation function. Kernel initializer, let's say it is 2. So 0 for GLOROT from normal distribution, 1 for GLOROT from uniform distribution, and 2 for Hay initializer from normal distribution, and 3 for Hay initializer from uniform distribution, right? So if it is 2, it means it will be Hay normal, right? Next, dropout rate. Dropout rate is a value between 0 to 1. So if it is 1, it means this layer will be dropped. And if it is less than 1, then this layer will be used, right? So let's say it is 0.2. So 20% of the neurons will be dropped while training the neural network. Now you see, this is one layer I have denoted. Similarly, I can denote the next layer. Similarly, I can denote n number of layers. So the maximum number of layers is n. But if the dropout rate is 1, then that layer will be dropped, means that layer will not be used. So you see, if you have fixed the maximum number of layers as 10, then your swarm and evolutionary algorithm will generate a deep neural network where the maximum number of layers will be 10. Minimum it can have 1 or 2 or 3 or any number between 1 to 10. Then once the layers are encoded into genes, then the deep learning model parameter, that is what is the learning rate, what is the batch size, what is the optimizer, that we have to keep in the genes, right? So learning rate is basically a real number, whereas batch size is represented in the power of 2 to the power k. If k equal to 1, it is 2. If k equal to 2, it is 4. If k equal to 3, it is 8, like this. And optimizer, if it is 1, then Adam optimizer. If it is 2, then AdaGrad. If it is 3, AdaDelta, like this. So like this, what we will do, we will encode a deep learning architecture into the chromosome of a particular swarm and evolutionary algorithm. Or you name it any swarm and evolutionary algorithm, it's just the changing of name, chromosome, or if it is differential evolution, then it is a vector. Then if it is a Whale optimization algorithm, then it is a Whale position. If it is a Gray Wolf optimization, then it is a search agent, like this. It's just a terminology difference, right? But it is encoded as a chromosome like this. Then what we will do, you see, this is a deep learning architecture. This is a deep learning architecture. This is a deep learning architecture. Then what we will do, we will obtain the fitness of the deep learning architecture. So we will obtain the fitness of the deep learning architectures. So fitness 1, fitness 2, fitness n. Okay. Then we will check the termination criteria. If the termination criteria is not satisfied, then we will use evolutionary algorithm operators. So in Whale optimization, there is only mutation operator, whereas in differential evolution, there is mutation and crossover operator. So these operators will be used to generate the next generation of deep learning architectures, right? So this process is repeated until the termination criteria is satisfied. So when the termination criteria is satisfied, the optimal deep learning architecture is used to forecast the test set. Okay, So this, so we have published one paper related to this, but here we have used only 3-layer ANN, right? But now I will show you a code where we are using n number of layers, and this can be extended to even 1,000 number of layers, right? So next one is Python code for swarm and evolutionary algorithm optimized DNN for time series forecasting. Okay, can I go for the code, dear participants? Dear
Sir,
participants,
would you please be kind to repeat it? Yes, sir.
will I go for the
So we'll now
Python
go
code?
to the code. Please, sir. Please, sir.
Yes.
Go ahead. Please, sir.
Okay, okay, okay. Okay. So here you see the first step is I have imported the packages, right? Whatever packages are required, I have imported. Then from Keras also, I have used TensorFlow as backend and Keras. So next one you see for mutation, here you see x0 plus f into x1 minus x2. So this is basically a differential evolution DE best one scheme, right? Next here, this one is bound checking. If it is more than the upper bound and lower bound, then it will check it. Then this is the crossover. So here we have used a DE best one bin binomial crossover we have used. Then we have splitted the time series into patterns. So you see the in time series by using a sliding window technique, we have converted it into a patterns, that is input and target patterns, right? Next, what we have done min max normalization. Min max normalization means transforming the data from one range to 0 to 1. So you see here, I can show you the formula. Original data minus mean to norm means original data minus minimum value divided by maximum value minus minimum value. So what it will do? It will convert the time series to a range between 0 to 1. Next, min max d norm. It will do what? Min max d norm will denormalize the time series, right? Denormalize the forecasted value. Means first we have converted into a range between 0 to 1. Then after processing it, then we will get the forecast in normalized range. But again, we have to scale it back to the original scale. Okay, so we will denormalize it. Then we have computed the accuracy measures. RMSE means root mean square error, find RMSE. Then we have computed the symmetric mean absolute percentage error, SMAPE. Then we have computed the mean absolute error. Then we have computed the MASE, mean absolute scaled error. So we have used 4 accuracy measures. Then you see activation function. So I have defined a function, get activation function. So if the number is 0, then it will return me ReLU activation function. If the number is 1, I will return sigmoid activation function. If the number is 2, then I will return 10H activation function, and otherwise it will return LU activation function. Similarly, kernel initializer, you see, if number equal to 0, then I will return the Glorot uniform kernel initializer. If the number equal to 1, I will return Glorot normal. If it is 2, I will return Hey normal, Hey uniform, and otherwise I will return Hey normal. Then you see then how I am computing the fitness. So find fitness LSTM1. So here I am, by using the LSTM model, you see I am dynamically generating the LSTM architecture. Sorry. So you see how I am dynamically generating the LSTM architecture. So here you see I have taken the model. So model is the sequential model. So those who know Python and have used TensorFlow and Keras, then it's a pretty simple one. So model equal to sequential. Now you see I am taking the first chromosome, that is chromosome of 0. Then I am rounding it off. So the chromosome value can be any real number between the upper bound and lower bound. Then I am rounding it up and I am storing a number. Okay, I am storing in a variable no. Then you see I am calling the get activation function and I am passing the chromosome 1. So if the chromosome 1 contains 2.3, then you see I am rounding it off. Means 2.3 will be converted to true. So 2 means I will call the get activation function. So get activation function 2 means it will return me 10H. So if that is 1, then it will return me sigmoid. So dynamically I am setting the activation function. Similarly, kernel initializer means from which range or from which distribution I will generate the initial value of weight set that I am determining. So here you see I am taking the chromosome 2, then I am rounding it off. So if it is, let's say, 1.2, so 1.2 means the round off value will be 1. So kernel initializer 1 means my GLOROT normal kernel initializer will be set, right? So next one is dropout rate. So dropout rate is denoted, you see, the chromosome 3 I am using as a dropout rate. Next one is, you see, if the dropout rate is not equal to 1. So if the dropout rate is 1, it means what? All the neurons are dropped. It means that layer is dropped. So if dropout rate is not equal to 1, then I am adding the model. So model.add LSTM, number means number of neurons, activation equal to act means, so from the chromosome whatever activation I will get, I will put it over here. Kernel initializer equal to ki means whatever kernel initializer I have got from the chromosome, that I will set. Similarly, the same thing I have done it for the second layer, and this can be done for n number of layers, right? Next, what I am doing, I am setting the deep learning model parameters, that is base size. So you see the 8th chromosome I am considering as the base size, and you see here I am done 2 to the power NP seal chromosome 8, means if chromosome 8 contains 2, then actually the base size will be 2 to the power 2, that is 4. Next, I am setting the learning rate over here, learning rate equal to 9. And you see here I have fixed the optimizer to Adam. But what you can do, you can take another chromosome, chromosome number 10, and you can set the values. If it is 0, then Adam. If it is 1, then RMS prop. If it is 2, then ADA grad, ADA delta, like this. Okay. Next, what I have done, I have compiled the model by using the all the parameters. Next, after the model is compiled, then I have fit the model by using the train data. Then I have predicted the output on the test data. Then finally, I am returning the output, right? So this is how you see I have converted the chromosome into a neural network model or into a deep learning model, right? So next, this is find fitness LSTM, means this, from this I will compute the predicted values, whereas from this I will compute the error, that is the fitness. You see here everything is same, only the return type is mean squared error y test y hat norm, whereas here you see the return value is pd.data frame y hat norm, means here I am returning the forecasted values only, whereas here I am returning the root mean square error. So you see, for finding the fitness, we have to use the accuracy measure. So here I have used mean square error as the accuracy measure. Once the find fitness accuracy measures are computed, then the best chromosome will be used to compute the forecasted value. And in that case, I will use find a fitness LSTM1, where it will return the predicted value, right? So now you see, let me go through the main module. So first I will read the time series. So leg length means number of inputs I have set to 12 because this is a monthly time series. Next, number of repetitions equal to 1. It can be set to anything. Length of train I have set. Length of validation, length of test I have set. Then you see I have normalized the time series. Then I have converted the time series into a pattern, get patterns. Then you see I have taken the model. You see I have taken 21, means I am using the LSTM model. I am not using CNN deep multilayer perceptron or GRU. Okay, so this is an automatic code that we have written so that every model can be run by using this code. Okay, so next one is, see, I have set the population size to 50. I have set the bounds. You see the first chromosome denotes what? Number of neurons. The lower limit is 2, the upper limit is 256. Means the number of neurons of the first layer will be between 2 to 256. Next, 0 to 3 means the activation function may be either 0. 0 means your LU activation function, 1 means sigmoid, 2 means your LU activation function, like that. And the kernel initializer I have set between 0 to 4, and similarly other values I have set. Then number of iterations I have set to 30. Then F, this is the edge I have told you that I am using DE best one evolutionary algorithm. So F equal to rand, I have used a random number, and crossover probability I have taken is 0.7. Then you see the population size denoting the deep learning architectures I have generated randomly. Then the fitness is evaluated of each architecture. Then the mutation, crossover and selections are repeated to obtain the best solutions. So now you see the best solution is denoted by the term best vector. Then I am predicting the future values. You see find fitness LSTM1 by giving the input X and output Y, length of validation and length of test, and the best vector. Best vector means best deep learning architecture to predict the future values. Then this Y norm 1, this is a normalized value. Then what I have to do? I have to denormalize it. So you see here I am denormalizing it. Min max denorm means I am denormalizing the forecasted values. Then what I am doing, I am computing the accuracy. Find RMSE will compute the root mean square error. Find SMAP will compute the symmetric mean absolute percentage error. And find MOE will compute the MAE and MASE, like that. I hope all of you are clear regarding this. Is that clear, dear participants?
Sir, can you show the
Yes, sir. Sir,
where
it's
this
very-
function is working?
Sir,
Okay.
hello. Honorable,
Yes, sir.
Honorable Institution, Shibrama, sir. Sir,
Yes,
actually, this
sir.
is Mustafa Shamim Freitas, one of the scholar, and the fact is actually that I'm working in the field of financial engineering. So
Yes,
this, deep learning and its application for multivariate time series analysis, it's very much, required for me.
Okay.
Okay,
So for
and so,
multivariate,
would you
sir, you
Yes,
see,
sir.
actually multivariate, what you can do, we can do by using single univariate one thing, and multivariate especially I will just go through briefly, because in this slide or in this session I have concentrated on univariate time series forecasting. Okay, for
I can
multivariate
understand that. I can understand.
I will touch upon that, how multivariate you can do it. Okay,
Okay,
I
okay.
will touch upon
But sir,
that.
my humble request to you is that it will be very, very kind of you. If you please be kind to share, some good reference book on multivariate,
Okay.
time series analysis through deep learning.
Okay,
Okay.
sir.
Thank you very much.
You take my email ID. You just
Okay.
drop me a mail. I will send you some good resources on multivariate time
Okay.
series forecasting using deep learning.
Okay. So would you
Okay.
please be kind to write it down on the chat box, please?
Okay. Okay. After completion of the session, I
Thank you
will
very much. Thank
write
you very
it.
much.
Okay, sir. Okay. Thank you. Okay. Okay.
So-
Can you move forward? Yes.
Actually, can you show us means from where this like optimizer? In case of optimizer, you are saying 0 is ADA and 1 is means delta. So where this
Yes.
updation is happening?
Okay, okay. Listen, this one I haven't shown it in this code. You see, as here I have shown you different activation functions. Here I have shown you different kernel initializers. Similarly, what you can do, you can take another cell over here, right? You can take another cell over here, and here you can define a function like this: get kernel or get optimizer, right? Get optimizer. Then here you see how many chromosomes I have used. I have used 9 chromosomes. You set just 10 chromosomes, right? And there you write down optimizer equal to
So I understand this one.
okay, okay,
Sorry,
chromosome 10.
means
Okay.
just I want to understand means how this updation is happening. Means from 0 to 1, in which code it is updating itself.
Okay, how the updation is out. Okay, let me explain you that one by help of this activation function. Okay, I think that will be the same one. Okay, so here
Yes,
you
sir.
see the activation function, you see get activation function chromosome 1. Okay, so chromosome 1 may have a real value between 0 to 4, right? Now whatever value I am getting, I am rounding it off. So rounding it off means, let's say it is 1.3. So round off means it will become 1. So get activation 1. Get activation 1 means which activation function it will return? It will return the sigmoid activation function. Similarly, what you can do, you can take a get kernel initializer, get optimizer. Then you set a value between a lower limit and an upper limit. Then you convert it into, round it off. You convert it into integer. Then you get the corresponding optimizer.
Okay, sir. Actually,
Your question is how
this
I am
yes, sir.
updating. How I
Yes,
am
sir. Yes,
updating.
it's calling one time. Get activation
Okay.
function is called one time. It will return one value. So for
Okay.
getting the
Next time.
next value,
Okay.
is it in
Next
the for
value.
loop?
Yes. You see, it is in the for loop. So you see, this is in the for loop. I in range ITER, right? So you see, for each candidate, what I am doing, I am calling the same function repeatedly. You see, A, B, C, population choice 3 replace false. Here, what I am doing, I am calling the, I am selecting 3 candidate solutions, A, B, C. Then I am calling the mutation. So this mutation will do what? It will generate another solution, okay, mutant vector. Or in your differential evolution, it is called as in differential evolution, it is called as mutant vector, right? So after that, this mutant vector bounds are checked, right? Then crossover operation is performed, right? Then by using that, we are computing the fitness of that one. Then we are performing the selection. If the objective of the current trial vector is better than the target vector, then we are replacing it, right? So now you see this process we are doing in a loop, you see, for iteration. So what it will do, first it will generate it will take 0th generation, then it will generate the first generation, then by taking first generation, it will generate the second generation. This process will go on. Okay, so you see, every time I am calling find fitness. So whenever I am calling the find fitness, you see find fitness LSTM. So here what I am passing the input, target, length of validation, length of test, and you see the trial. Trial means what? Trial vector. Okay, I hope your doubt is clear.
Yes, yes, sir.
You see, I am doing
So
it
is
in a
it
loop.
possible to share the screen? No, sorry, code.
You see, this is under review right now. Okay.
Okay.
So, okay, I will share my code. You can get it from GitHub. Okay, once it is published. Okay.
Yes, thank you.
Okay, thank you. Okay. Okay, next. So now you see what the authors have done. They have used statistical models. They have used deep learning models. But the statistical models are good at capturing the linear pattern, whereas deep learning models are good at capturing the non-linear pattern. However, most of the real world time series are neither purely linear or not purely non-linear. It contains a combination of linear and non-linear patterns. So what they are doing, the authors have used, or I have also published many papers by hybridizing statistical models with the deep learning models. So what they do, there are basically 4 approaches that I will discuss today, and there are only these 4 approaches available in the literature also. So first they take a time series, then they apply it on a linear model like a statistical model like ARIMA or exponential smoothing like this. So once they apply a linear model on it, they obtain the linear forecasts. So here they obtain linear forecasts. So this linear forecast, they subtract from the original time series to obtain the residual series. Now what they do, the residual series, you see, the time series consists of a linear component and a non-linear component. So this is the linear component and this curved line is the nonlinear component. So if you will subtract this linear component, what you will get? You will only get a non-linear component. So nonlinear component can be efficiently modeled by using a nonlinear deep learning model. So the residual series considering as nonlinear, a nonlinear deep learning model is applied and the deep learning model forecasts are obtained. Then the linear forecasts are added with the nonlinear model deep learning forecast to obtain the final forecasts, right? So here you see, here we are adding the forecast and here we are obtaining the residual series by subtracting. The other way what you can do, so this is an additive hybrid model. Another one is multiplicative hybrid model. In multiplicative hybrid model, what they do, they apply a linear model and they obtain the linear forecast. Then they divide the linear forecast from the time series to obtain the residual series. Then the residual series modeled by using nonlinear deep learning model. So you see here what you can do, you can use the swarm and evolutionary algorithm optimized deep learning model so that you can get a better forecast. Next, what you can do, you can multiply the nonlinear deep learning forecast with linear model forecast to obtain the final forecasts, right? So contrasting to these additive and multiplicative models, where in series we are applying the models, we can apply the models in parallel. So what you can do, we can apply n number of models parallelly. So model 1, model 2, model n we have applied, and we have computed the forecast 1, forecast 2, forecast n. Next, what we will do, each forecast we will give some weight, f1 into w1 plus f2 into w2 plus dot 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 plus fn into wn. So now you see, if we will get this, then we will get the final forecast. So now here the important term is how to get these weights. So there are three possible ways. First one is equal weight. Equal weight means what you will do? You will add this and divided by n. This is equal weight. Second one is variable weight. Variable weight means what? This weight will be, let's say 0.1, this weight may be 0.3, this weight may be 0.5, like this. So now the question is how to obtain the weights. So these weights can be obtained by using swarm and evolutionary algorithms, right? So what you will do, you will encode the weights into the chromosomes. So W1, W2, dot 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 Wn. This is one set of weights. Then similarly, again you can encode W1, W2, W11. Let me make it W11, W21, Wn1, W21, W22, dot 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 Wn2 or W2n, right? Similarly, you can encode the weights, then you can apply the mutation, crossover and selection operators to generate the next generation weights. And this process continues until the termination criteria is satisfied. When the termination criteria is satisfied, the optimal weight can be used, or the best weight of the final generation can be used to obtain the ensemble of weights. And the third one is, so this is equal weight, variable weight, and third one is time varying weight. So equal weight means what? This, you see, this is a time series. Okay, let me show you one thing. Let me show you this one. Okay, so here you see, here I have used a time series, and you can see that here I have used a ARIMA forecast. Okay, so you see ARFIMA forecast, theta forecast, naive forecast, lasso forecast, CNN forecast, LSTM forecast, and this is the original time series. Now you see here I have used 6 models, so I will get 6 weights, right? So you see this weight will be, let's say the first weight is 0.1, 0.2, like this, the weights are. But you see this weight is fixed for the first row, this weight is fixed for the second row, this weight is fixed for the third row, this weight is fixed for the fourth row, and all the rows. It means the weights are fixed for all the time duration, or for all the time period, or all the time interval. Whereas time varying weights, what you will have, in time varying weights, here 0.1, 0.2 means here you might have 0.3, here you might have 0.5. And here for the next time period, the weight may be 0.01, and here it might be 0.23, right? So you see, this is called as your time varying time varying weights. Okay, and this can be time varying weights can be obtained by using your Kalem filter or by using your hidden Markov model, right? So due to lack of time, I am not going to that. And the next one is MATLAB code for this one. I think time will not permit me to show you this one. So I will go to the next topic. The another one is decomposition based time hybrid models. So here what we will do, first we will decompose the time series into n components by using empirical wavelet transform or variational mode decomposition or empirical mode decomposition or ensemble EMD or CEMDN. So once we have got the individual components, then we will check which model is appropriate for that one. Then for each component, we will use a independent model. Then we will get the forecast on independent components. Then what we will do, again we will use the same thing. We will assign weights to independent components by using different models, and we can ensemble the forecast. So here also swarm and evolutionary algorithms can be used to obtain the weights for the ensemble. And the next one is, so these are some papers we have published relating to hybrid models. Right? The next one is fuzzy time series forecasting. So the time series can be converted to fuzzy domain, operate in the fuzzy space, then again it can be transferred back to the crisp domain to be used in the practical domain. So how will you do it? So it consists of basically 5 steps. The first one is the universe of discourse for the time series is determined, and the number of intervals or length of intervals are determined. So if a time series, let me take a time series from 10 to 50, let's say temperature time series. So first what I will do, I will compute the universe of discourse. So universe of discourse is nothing but the minimum value minus a particular value. Let's say the temperature, usual temperature is from 10 to 50 degree. So universe of discourse, we may consider that 10 minus 10, 0 degree, and maximum temperature is 50 plus 10, 60 degree. So first the universe of discourse is identified, then the universe of discourse is split into number of intervals. Let's say I have taken the universe of discourse as 0 to 60, then if I have split it by taking an interval of 10, so I will have 6 intervals, 0 to 10 very low temperature, 10 to 20 low temperature, 20 to 30 medium temperature, then 30 to 40 high temperature, 40 to 50 very high temperature, 50 to 60 very high temperature. So sorry. So what I can do, I can convert this crisp time series to a fuzzy time series by using fuzzification technique. Then what I will do, I will, after I have got the fuzzy time series, then the order of the fuzzy time series model will be determined by analyzing autocorrelation or partial autocorrelation function of the series. Then the time series will be converted into input and target patterns by using sliding window. So once it is converted into sliding window, that is called as, in fuzzy term, it is called as fuzzy logical relationship. This fuzzy logical relationship will be modeled by using deep learning models, or you can use swarm and evolutionary algorithm optimized deep learning models for doing fuzzy time series forecasting. So once the forecasts are obtained, those are fuzzified forecasts, you have to defuzzify them, then you have to measure the forecasting accuracy. Next, these are some slides. Let me skip it. Python code, let me skip it again because of lack of time. And these are some publications we have made using fuzzy time series forecasting employing deep learning models. Here, let me tell you, in this publication, we have used traditional fuzzy set without considering membership values. Here we have used traditional fuzzy sets by considering membership values. Here we have used intuitonistic fuzzy set, and here we have used neutrosophic fuzzy set. And recently in 2023, we have published one article by using hesitant fuzzy set. So let me just give a quick look into this one. So in traditional fuzzy set, what we do, we just consider the membership values. Tomorrow it will be a rainy day or sunny day. Suppose you are telling that 0.7 sunny day. So the membership value is 0.7. But now if I will ask you the opposite question, whether tomorrow is a rainy day, what is the membership? So 0.7, 1 minus 0.7, you may tell that 0.3. But if you have some confusion or if you have mind, you might tell that 0.1 rainy day. Means 0.7 you are telling sunny day, 0.1 you are telling as rainy day. So the 0.7 plus 0.1. So what is the remaining? 0.2. So 0.2 your hesitation, means you are unsure about that whether it is a rainy or sunny day. So you see, by considering membership and non-membership, if you are modeling the time series, then it is called as intuitionistic fuzzy time series. And if you are considering membership, let me write it over here, membership, non-membership and hesitancy, these three things, then it is called as hesitant fuzzy time series. And here you see in hesitant fuzzy time series, the sum of membership, non-membership and hesitancy is 1, whereas in neutrophobic time series, the sum of membership, non-membership and hesitancy is 3, which are independent of each other. So by considering these things, we have proposed some things and we have published it. And if I will go through the bigger picture, as Sar is asking, so the time series forecasting can be done by univariate and multivariate. So I have discussed all the univariate things right now. Okay, all these univariate things right now. But let me quickly conclude regarding multivariate things. Multivariate means if multiple number of time series are affecting a particular time series, then that is called as a multivariate time series. So there what you can do, you can have direct application of model. Suppose there are k number of independent variables which is affecting the dependent time series. So what you will do, you can directly feed the k inputs to a particular model and you can predict the outputs, but that might not give you the better result. So what you can do feature engineering, right? Dimensionality reduction. So in dimensionality reduction, what you can do, either you can use PCA or you can use LDA, linear discriminant analysis, principal component analysis, or you can use ICA, independent component analysis, or you can use TSNE, T stochastic neighborhood embedding. So these 4 methods can be used to reduce the dimensionality or to transform the dimensionality. Then on the reduced or transformed dimensionality, you can apply the deep learning models, which can be optimized by using the Swarm-End evolutionary algorithms, as I have told, right? And another one is feature selection. So feature selection is again of 3 types. One is filter method. So in filter, what you will do, you will use correlation coefficients and ranking of features. And another one is wrapper. So in the wrapper method, what you can do, you can use the swarm and evolutionary algorithms to select the features, right? Then after selection of features, then you can apply any particular model and you can optimize that model by again using swarm and evolutionary algorithms, and you can get better result. Next, otherwise you can use filter, wrapper or embedded methods. So embedded are the mixing of this filter and wrapper methods, right? So by using this, you can do multivariate time series forecasting. Again, lack of time, I haven't elaborately kept it in my slides. Okay, so next one is drawback of gradient based optimization techniques. So Sanjay sir, will I continue?
Yes, sir, you can take another 5 minutes.
Okay, thank you. So you see, up to now, what we have done, we have used deep learning models and we have optimized the parameters of deep learning models using swarm and evolutionary algorithms. Another thing that is required in near future, the gradient based optimization algorithms have several drawbacks. For example, you see, if I will start my initial value from here, so it is subjected to initial values. As initial values are randomly generated, so it depends on the initial values of algorithmic parameters. But if I am fortunate enough, if my weight sets are generated from here, I will go to the global optimum. right? And so this is one problem, sensitive to initial values of algorithmic parameters, the gradient based algorithms. And the second one is, as we are computing the gradient, your activation function must be differentiable. Okay, so that is another limitation. And second one is the learning rate. So you see, if the learning rate is too slow, then what we will do, the convergence will be very slow. But if the learning rate is too high, you see in this case, it will form oscillation. Okay, although you see the global optima is here, but as the learning rate is high, it will oscillate around the global optima, right? So the drawbacks are, activation function must be differentiable. Speed of training depends upon how easily you can differentiate the activation function. Training performance is subjective to sensitive of initial values of weight set. Slow convergence and chances to trapping to local optima is high. In order to avoid this, what you can do, you can use swarm and evolutionary algorithms to replace the gradient based optimization algorithms. So in swarm and evolutionary algorithms, what we do, we start with a set of solutions, then we apply mutation and crossover in such a way that we will try to reach the global optima, and the chances of reaching the global optima is high. So how can you do this for obtaining the weights of neural network? So for that, what I will do, we will represent the weights and bias of the neural network as the genes of the chromosome. So let me take a simple shallow neural network. Okay, so here you see these are the 4 weights. So I have encoded it into the chromosome. Okay, next another 4 weights I have encoded it into the chromosome. And then again, weights between hidden to output layer, I have encoded it in the chromosome. Then the biases I have encoded. Then the bias of output layer I have encoded. Now you see, we are representing the weights of the neural network as the chromosome of a swarm and evolutionary algorithm. Then what we will do, we will give the inputs and feed forward the inputs. So now you see, we will give the inputs and feed forward the inputs, compute the outputs, and based on that, we will compute the fitness. So this is how you can compute the fitness. You can encode the weights as the chromosomes of the swarm and evolutionary algorithms and compute the fitness. Then again, by using mutation, crossover, and selection, you will update the weights, and these weights are updated until a termination criteria is satisfied. And when the termination criteria is satisfied, then the chromosome of the final generation having the best fitness is used as the near optimal weight set of NN. Okay. So with this, I will conclude. Thank you. Any doubt?